For 165 million years, dinosaurs weren't just Earth's dominant animals. They were the blueprint for survival itself. From chicken-sized hunters in the Triassic scrublands to 100-ton sauropods that made the ground shake with each step, these creatures adapted, evolved, and thrived through climate shifts that would have ended most lineages. They survived the Triassic-Jurassic extinction that wiped out 76 of all species. They diversified into over 1,000 known species across every continent. They developed feathers, complex social behaviors, and body plans so successful that birds, living dinosaurs, still outnumber mammals today. Yet in a geological instant 66 million years ago, a 10-kilometer asteroid traveling 20 kilometers per second ended their reign. This is the complete timeline of the dinosaurs, their rise from obscurity, their 165 million year dominance, and the catastrophic event that rewrote life's rulebook forever. Silence. That's the sound of Earth 252 million years ago, in the immediate aftermath of the worst catastrophe the planet has ever known. The Permian-Triassic extinction event, known to paleontologists as the Great Dying, had just concluded its assault on life itself. Volcanic eruptions in what is now Siberia had been pumping carbon dioxide into the atmosphere for roughly a million years, releasing an estimated 100,000 billion metric tons of the greenhouse gas. The result was a global temperature increase of approximately 10 degrees Celsius, turning a world with cold temperate zones and tundra at the poles into one where polar regions became temperate and equatorial latitudes baked under relentless heat. By some estimates, up to 90 of all species vanished. In the oceans, oxygen levels plummeted as warming waters could no longer hold dissolved gas in sufficient quantities. Trilobites, ancient armored arthropods that had crawled across the seafloor for nearly 300 million years, disappeared entirely. On land, the dominant mammal-like reptiles, synapsids that had ruled terrestrial ecosystems throughout the Permian, were decimated. Many insect lineages, which typically survive extinction events better than vertebrates, were wiped out. Even plants took a catastrophic hit. The first few million years of the Triassic period are marked by an absence of coal deposits, suggesting that peat-forming vegetation had collapsed so thoroughly that it simply wasn't accumulating. What remained was a supercontinent called Pangaea, a C-shaped landmass stretching from pole to pole and surrounded by the vast Panthalassa Ocean. The interior of this megacontinent was one of the most inhospitable places in Earth's history, a massive desert system where temperature extremes define existence. Without large bodies of water to moderate climate, the heart of Pangaea experienced scorching summers and frigid winters. Seasonal monsoons lashed the coastal regions, driven by the temperature differential between the supercontinent's massive bulk and the surrounding ocean, but those rains rarely penetrated far inland. Yet life, as it always does, persisted. In the barren landscapes of the early Triassic, survivors clung to existence. Among them was Lystrosaurus, a pig-sized herbivorous synapsid with a beak-like snout and stubby tusks. Fossil evidence suggests these creatures became extraordinarily common in the years following the extinction, so common that their bones dominate early Triassic rock formations across multiple continents. They represent what ecologists call a disaster taxon, a species that thrives in the ecological void left behind when more specialized competitors vanish. But Lystrosaurus and the other mammal-like reptiles were not alone. Somewhere in this recovering world, a lineage of reptiles called archosauromorphs, diapsids with two temporal openings in their skulls, was quietly adapting to the new conditions. These creatures had survived the extinction, and from them would emerge a group that would redefine what it meant to dominate the planet. The early Triassic, spanning from approximately 252 to 247 million years ago, was a time of ecological experimentation and recovery. In the immediate aftermath of the extinction, ecosystems were stripped down to their simplest components. The dominant land vertebrates were a group called Lystrosaurus, tusked dicynodonts that resembled a cross between a pig and a reptile. Fossils of Lystrosaurus comprise up to 95 of vertebrate specimens in some early Triassic deposits across Antarctica, South Africa, Russia, China, and India, suggesting these herbivorous synapsids were among the few creatures capable of thriving in the harsh post-extinction world. But their dominance was temporary. As the climate stabilized and vegetation began to recover, new players entered the stage. By the Middle Triassic, roughly 247 to 237 million years ago, archosauromorphs had begun their evolutionary radiation in earnest. The archosauriforms, a subset distinguished by more upright limb postures and active predatory lifestyles, produced several lineages that would come to define Triassic ecosystems. Erythrosuchids were among the earliest large predators, some species reaching lengths of 5 meters with massive skulls and powerful jaws lined with serrated teeth. These creatures were apex predators in the early recovery phase, but they were transitional forms, still retaining a somewhat sprawling gait. More derived with the true archosaurs, which appeared in the early Triassic and split into two major branches that would shape the future of vertebrate life, Pseudosuchia, the lineage leading to modern crocodilians, and Avametatarsalia, the lineage that would eventually produce pterosaurs and dinosaurs. The Pseudosuchians were remarkably successful during the Triassic. They diversified into an array of ecological roles that would seem bizarre by modern standards. Aetosaur were heavily armored herbivores resembling armadillos, their backs covered in interlocking bony plates called osteoderms. Rauisuchians were massive terrestrial predators, some exceeding 10 meters in length, with skulls built for crushing bone. Phytosaurs were crocodile-like ambush predators that dominated rivers and lake margins, their long snouts filled with conical teeth perfect for snatching fish and unwary prey at the water's edge. For much of the Triassic, these Pseudosuchians were the dominant large animals. Dinosaurs, when they finally appeared, were not the rulers of their world. They were minor players, small and relatively uncommon, living in the shadow of their Pseudosuchian cousins. The environments they inhabited were shaped by Pangaea's geography. With all landmasses fused into a single supercontinent, ocean currents and atmospheric circulation patterns were fundamentally different from today. The interior of Pangaea was isolated from moderating oceanic influences, creating extreme continentality, scorching summers, freezing winters, and minimal rainfall. The western coast of Pangaea, facing the massive Panthalassa Ocean, received seasonal monsoons of extraordinary intensity. Vegetation was patchy and often restricted to river valleys, coastal regions, and high-latitude areas where conditions were more temperate. There were no flowering plants yet. The flora consisted of ferns, cycads, conifers, and seed ferns. The fossil record from formations like the Maltino Formation in South Africa and the Chile Formation in North America preserves evidence of these plant communities, as well as the early archosaurs that moved through them. But the archosaurs possessed something their competitors did not, a suite of anatomical innovations that would prove decisive in the long run. Their limbs were positioned more directly beneath the body, reducing energy expenditure during locomotion and allowing for greater endurance. Their skulls featured openings called fenestrae that reduced weight while maintaining strength and provided space for larger, more powerful jaw muscles. Many archosaurs developed more complex respiratory systems, with air sacs that increased oxygen exchange efficiency, a feature that would later become crucial for the energetic demands of large body size and, eventually, flight. These were not dramatic advantages in the short term, but over millions of years, they compounded. By the late Triassic, around 237 to 201 million years ago, the stage was set for a major transition. Archosaur diversity had exploded. Pseudosuchians dominated most terrestrial niches, but the Avametatarsalia, the dinosaur line, were beginning to appear in the fossil record. These early forms were small, bipedal, and unremarkable in appearance. They did not overthrow the Pseudosuchians through competition. They simply persisted, occupying marginal roles, waiting for an opportunity that would come not from their own superiority, but from the planet itself. The late Triassic world, between 237 and 201 million years ago, represented the peak of archosaurian diversity, but was also a world on the edge of another transformation. Climate patterns were shifting. Pangaea, which had begun to show signs of rifting, was experiencing increased tectonic activity along what would become the Atlantic Ocean. In regions corresponding to modern-day eastern North America, northwestern Africa, southwestern Europe, and South America, the supercontinent was literally tearing apart. Magma pushed upward through crustal fractures, pooling in massive chambers beneath the surface. This process, driven by mantle plumes and continental extension, was building toward one of the largest volcanic events in Earth's history, the Central Atlantic Magmatic Province, or CAMP. The ecosystems of the late Triassic were rich and complex. In what is now the American Southwest, preserved formations like the Chinle fossil assemblages reveal a world of giant phytosaurs lurking in rivers, herds of armored Aetosaur browsing on low vegetation, and massive Rawasuchian predators stalking the floodplains. Small dinosauromorphs, animals closely related to true dinosaurs, scurried through the underbrush. True dinosaurs were present but rare, comprising less than 10 of vertebrate fossils in most late Triassic assemblages. They were small, typically 1 to 2 meters in length, bipedal, and carnivorous or omnivorous. There is no indication that these creatures were destined for dominance. The Pseudosuchians held every major ecological role. If someone had observed the late Triassic world and been asked to predict which lineage would rule the Jurassic, dinosaurs would not have been the obvious choice. But around 201.4 million years ago, the rifting of Pangaea reached a critical threshold. The Central Atlantic Magmatic Province began its eruptive phase. This was not a single volcano or even a cluster of volcanoes. It was an event of planetary scale. Across an area exceeding 11 million square kilometers, basaltic lava erupted from fissures in the crust, flooding vast regions with molten rock. Individual lava flows extended for hundreds of kilometers. The volume of magma produced was staggering. Estimates suggest approximately 2 to 3 million cubic kilometers of basalt were emplaced over a period of roughly 600,000 years, with the most intense activity concentrated in the first 40,000 years. The environmental consequences were catastrophic. Carbon dioxide emissions from the eruptions drove atmospheric concentrations upward by an estimated 100,000 gigatons. Global temperatures increased by 10 to 15 degrees Celsius within a geologically brief interval. The oceans absorbed massive quantities of this carbon dioxide, causing seawater pH to drop precipitously, a phenomenon known as ocean acidification. Marine organisms with calcium carbonate skeletons, particularly those with aragonitic shells like corals and certain mollusks, experienced dissolution and growth inhibition. Coral reefs collapsed. Additionally, the warming oceans lost their capacity to hold dissolved oxygen, creating widespread anoxic conditions, zones where oxygen levels fell too low to support most animal life. In some regions, the oceans became euxinic, saturated with hydrogen sulfide, a toxic compound fatal to most organisms. On land, the effects were equally devastating. The combination of extreme heat, acid rain for volcanic sulfur emissions, and possible ozone layer depletion created hostile conditions for many groups. Mercury concentrations in sediments from the Triassic-Jurassic boundary show massive spikes, consistent with volcanic outgassing and environmental poisoning. Plant communities underwent radical restructuring. Pollen records show abrupt shifts in dominant species, with many late Triassic plant families disappearing from the fossil record. Carbon isotope excursions, sudden shifts in the ratio of carbon-12 to carbon-13 preserved in organic matter and carbonates, mark the boundary interval, indicating massive disruptions to the global carbon cycle that lasted for hundreds of thousands of years. When the dust settled, approximately 76 of all species had vanished. In the oceans, 23 to 34 of marine genera disappeared, including all conodonts, eel-like vertebrates with complex tooth structures that had existed for over 300 million years. On land, nearly all large non-dinosaurian archosauromorphs were extinct. The Rawasuchians, the Aetosaur, the phytosaurs, gone. The dominant Pseudosuchian groups that had ruled Triassic ecosystems for tens of millions of years were reduced to a handful of surviving lineages, most of which would eventually give rise to modern crocodilians. Mammals, which had also appeared in the Triassic as small, nocturnal insectivores, survived. Pterosaurs survived. And dinosaurs, those small, marginal creatures that had comprised less than a tenth of late Triassic vertebrate diversity, survived. The world that emerged in the early Jurassic, beginning 201 million years ago, was fundamentally different. The ecological roles once filled by pseudosuchians were now vacant. Dinosaurs, for reasons still debated by paleontologists, were among the groups best positioned to exploit this emptiness. Perhaps their upright stance provided an energetic advantage in the hot post-extinction world. Perhaps their respiratory systems, already more efficient than those of many competitors, allowed them to thrive in environments with fluctuating oxygen levels. Or perhaps they were simply lucky, survivors of a catastrophe that eliminated their primary competitors. Whatever the reasons, the Jurassic would belong to them. The question of when dinosaurs first appeared is deceptively complex. The fossil record, fragmentary by nature, offers only glimpses of evolutionary transitions that unfolded over millions of years. What paleontologists can say with confidence is that by the Middle Triassic, around 240 million years ago, the Avimetatarsalian lineage, the branch of archosaurs that would eventually produce both pterosaurs and dinosaurs, had already diverged from their pseudosuchian cousins. But these early Avimetatarsalians were not yet dinosaurs in the technical sense. They were dinosauromorphs, creatures that shared certain skeletal features with true dinosaurs but lacked the complete suite of characteristics that defined the group. Fossils like Merosuchus and Lagerpetin from Argentina, dating to approximately 236 million years ago, show animals with elongated hind limbs, reduced forelimbs, and bipedal postures, adaptations that suggest they were fast, agile runners. These were the ancestors, the evolutionary precursors standing at the threshold of a revolution they would never see completed. The oldest confirmed dinosaur fossils date to approximately 233 to 231 million years ago, from the Carnian stage of the late Triassic. These specimens come primarily from the Esquigualasto Formation in Argentina and the Santa Maria Formation in Brazil, rock layers that preserve a world radically different from anything existing today. The climate was warm and seasonal, with pronounced wet and dry periods driven by monsoonal circulation patterns. Rivers meandered across floodplains, bordered by forests of conifers, seed ferns, and cycads. Volcanic ash layers interspersed throughout these formations provide precise dating horizons, allowing paleontologists to place these early dinosaurs in a well-constrained temporal framework. And what the fossils reveal is striking. The first dinosaurs were small, lightly built, and anatomically unremarkable compared to the dominant archosaurs of their time. Eoraptor linensis, discovered in the Esquigualasto Formation in 1991, is one of the earliest known dinosaurs, dating to approximately 231 million years ago. The nearly complete skeleton measures just over 1 meter in length and likely weighed around 10 kilograms, about the size of a medium dog. Its skull is small and narrow, with large eye sockets indicating well-developed vision. The teeth are heterodont, meaning they vary in shape along the jaw. Some are blade-like with serrations suitable for slicing meat, while others are more leaf-shaped, suggesting a diet that included plant material. This dental arrangement has led paleontologists to classify Eoraptor as either a primitive theropod or a basal saurischian, a member of the broader group that would eventually split into theropods and sauropodomorphs. The hands retain 5 digits, though only the first 3 bear claws of significant size, a configuration that would later become standard in theropods as the outer 2 digits progressively reduced. Herosaurus esquigualastensis, also from the Esquigualasto Formation and roughly contemporaneous with Eoraptor, represents a more robust early dinosaur. Adults reach approximately 3 to 6 meters in length and may have weighed between 200 and 350 kilograms. Unlike Eoraptor, Herosaurus was unambiguously carnivorous, with a skull designed for predation, deep and narrow, with blade-like teeth bearing prominent serrations on both front and rear edges, ideal for slicing through flesh. The lower jaw possessed a unique joint that allowed the mandible to flex slightly, enhancing the grip on struggling prey. The forelimbs were relatively short but powerful, tipped with large curved claws. The hind limbs were long and muscular, indicating that Herosaurus was a swift, bipedal runner capable of pursuing prey across open ground. Yet despite these predatory adaptations, Herosaurus and its contemporaries were non-apex predators in their ecosystems. That role was occupied by Rauisuchians, massive pseudosuchian archosaurs that reached lengths of 8 to 10 meters and possess skulls over a meter long. Fossils of Saurosuchus galilei, a Rawasuchian from the same formations that yielded early dinosaurs, reveal an animal built on an entirely different scale, heavily muscled limbs, a deep rib cage, and jaws capable of generating bite forces that could crush bone. In this context, early dinosaurs were mid-tier predators at best, occupying ecological niches as hunters of smaller prey, lizard-like reptiles, early mammals, insects, and possibly juvenile archosaurs. The idea that dinosaurs burst onto the scene and immediately dominated is contradicted by the fossil evidence. They appeared, they persisted, but they did not rule. What, then, allowed these early dinosaurs to survive in a world dominated by larger, more established competitors? The answer lies in anatomy, subtle structural features that provided incremental advantages. Dinosaurs possessed fully upright limb postures, with legs positioned directly beneath the body rather than sprawling outward. This configuration reduced the energy cost of locomotion and enabled sustained speeds over long distances. The hip socket was perforated, creating a more efficient ball-and-socket joint that allowed for a greater range of motion. The ankle joint was modified into a simple hinge, eliminating unnecessary lateral movement and increasing stride efficiency. The vertebrae in the hip region were fused to the pelvis, forming a rigid structure called the sacrum that provided stability and strength for bipedal locomotion. These were not revolutionary changes individually, but collectively they made dinosaurs highly efficient walkers and runners. The respiratory system also differed. While direct evidence of soft tissue was absent in these early forms, comparisons with later dinosaurs and modern birds, living dinosaurs, suggest that even primitive dinosaurs may have possessed more efficient breathing systems than their contemporaries. Modern archosaurs, including crocodilians and birds, have unidirectional airflow through the lungs, a system more efficient than the bidirectional tidal breathing of mammals. Birds take this further with air sacs that extend throughout the body, reducing weight and increasing oxygen exchange. Skeletal evidence in later dinosaurs shows pneumatic cavities in bones where air sacs would have been housed. If early dinosaurs possessed even rudimentary versions of these systems, it would have given them a metabolic edge, allowing for higher activity levels and better endurance. But perhaps the most important factor was not superiority, but adaptability. Early dinosaurs were generalists in many respects. They were small enough to exploit resources unavailable to larger predators, fast enough to avoid becoming prey themselves, and anatomically flexible enough to diversify when opportunities arose. The late Triassic world was stable. Pseudosuchians had settled into established ecological roles, and there was little room for newcomers to expand. Dinosaurs remained in the shadows, comprising less than 10 of vertebrate fossils in most Carnian and Norian formations. They were not thriving spectacularly. They were simply surviving, filling niches that were not already occupied, waiting for circumstances to change. By the late Carnian and into the Norian stage, approximately 227 to 208 million years ago, dinosaur diversity had begun to expand, albeit slowly. The Saurischian lineage, one of the two major dinosaur groups, distinguished by a lizard-like hip structure where the pubis points forward, had split into two distinct branches. Theropods, the predominantly carnivorous bipedal dinosaurs, continue the body plan established by Herosaurus, upright stance, grasping hands, and teeth designed for meat eating. Early theropods remained relatively small, most under 3 meters in length, occupying roles as agile hunters of smaller vertebrates and possibly scavengers of larger carcasses left by Rawasuchian predators. The second Saurischian branch, the sauropodomorphs, represented a radical departure from the theropod template. These dinosaurs were experimenting with herbivory, a lifestyle that would eventually produce the largest land animals in Earth's history. The earliest sauropodomorphs, called prosauropods, appeared in the late Triassic and displayed a transitional anatomy. Plateosaurus, known from over 100 specimens found primarily in Germany, France, and Switzerland, lived approximately 214 to 204 million years ago and reached lengths of 5 to 10 meters with estimated weights between 600 and 4,000 kilograms, depending on the specimen. Unlike their theropod cousins, prosauropods had longer necks, smaller heads relative to body size, and teeth that were more leaf-shaped than blade-like, adaptations for cropping and processing plant material. Their hands retained large thumb claws, possibly used for defense or manipulating vegetation. The limb proportions suggest Plateosaurus could move both bipedally and quadrupedally, though which mode was preferred remains debated among paleontologists. The second major dinosaur group, Ornithischia, characterized by a bird-like hip structure where the pubis points backward, also emerged during the late Triassic, though their fossil record from this period is considerably sparser. The earliest confirmed ornithischians, such as Pisanosaurus from Argentina, dating to approximately 228 million years ago, were small bipedal herbivores with distinctive features that would define the group. A predentary bone at the tip of the lower jaw that formed a beak-like structure, and teeth with features indicating they were designed for grinding plant material rather than slicing meat. These early ornithischians were unremarkable in size and appearance, typically 1 to 2 meters long, but they represented the ancestral stock that would eventually diversify into armored ankylosaurs, horned ceratopsians, and duck-billed hadrosaurs. What united all these early dinosaurs across both major lineages was their relative scarcity. Fossil assemblages from the late Triassic paint a consistent picture. Pseudosuchians remained numerically and ecologically dominant, while dinosaurs comprised a minority of large vertebrate specimens. At the Esquigualasto Formation, for example, dinosaurs represent approximately 6 of the identifiable vertebrate fossils, with the remainder consisting primarily of various pseudosuchian groups. In the slightly younger Los Colorados Formation, also in Argentina and dating to the Norian stage around 215 million years ago, dinosaur representation increases to about 30, a significant jump, but still not dominance. The trend suggests gradual expansion rather than sudden takeover. Dinosaurs were slowly increasing in diversity and abundance throughout the late Triassic, but they had not yet displaced their Archosaurian competitors. Their anatomical advantages, while real, were not overwhelming in the context of late Triassic ecosystems. The upright limb posture improved locomotor efficiency, but Rauisuchians had evolved similar adaptations independently. The perforate hip socket reduced weight and improved mobility, but this alone did not grant superiority over larger, more powerful predators with established territories and prey bases. The modifications to the ankle and foot improved running speed, but many pseudosuchians were also capable runners. What dinosaurs possessed was not dominance through competitive superiority, but resilience through anatomical versatility, features that would prove decisive not in stable times, but during catastrophic upheaval. They were survivors, adapted not for conquest but for persistence, and when the world changed violently at the end of the Triassic, that resilience would matter more than raw competitive ability. The late Triassic presented a paradox. Dinosaurs were diversifying and becoming more common, yet they remained subordinate to their pseudosuchian relatives. Footprint evidence from this period provides additional insight into their abundance and behavior. Trackways preserved in sedimentary rocks from locations such as the Newark supergroup in eastern North America and similar formations in Europe and Africa show that small to medium-sized dinosaurs were moving through late Triassic landscapes in considerable numbers. These trace fossils sometimes outnumber skeletal remains, suggesting that dinosaurs may have been more abundant than body fossils alone indicate. However, interpreting trackways is complex. A single animal can create multiple tracks, and not all tracks are preserved equally. What the footprints do reveal is that dinosaurs were active, mobile, and capable of traversing varied terrain from river margins to semi-arid floodplains. The social behavior of these early dinosaurs remains largely speculative, as soft tissue and behavioral evidence rarely fossilize. However, some trackway sites preserve multiple parallel sets of footprints moving in the same direction, which paleontologists interpret as possible evidence of group movement, though whether this represents coordinated social behavior, family groups, or simply multiple individuals using the same travel routes is impossible to determine definitively. Skeletal evidence offers limited clues. Some early dinosaurs show variations in size and robustness that may indicate sexual dimorphism, with larger, more heavily built individuals possibly being males competing for mates or territory. Growth rings in fossilized bones, similar to tree rings, suggest that many early dinosaurs experienced seasonal growth patterns, putting on mass rapidly during favorable periods and slowing growth during times of resource scarcity. Their dietary strategies were becoming increasingly specialized. Theropods remained committed carnivores, with tooth morphology and jaw mechanics optimized for processing meat, where patterns on theropod teeth show scratches and pits consistent with bone contact, indicating they were actively feeding on vertebrate prey and possibly engaging in scavenging behavior. The prosauropods, by contrast, showed dental wear patterns suggesting they processed tough plant material. Their teeth exhibit flat were surfaces created by grinding vegetation, and their jaws lacked the precise occlusion, tooth-to-tooth contact, that would develop in later herbivorous dinosaurs. Instead, they likely used a combination of cropping with their jaws and possibly gastric processing with stones called gastroliths, smooth rocks found in association with some prosauropod skeletons that may have functioned like a bird's gizzard, grinding plant material in the stomach. The geographic distribution of late Triassic dinosaurs was limited primarily to Gondwana, the southern portion of Pangaea that would eventually break apart into South America, Africa, India, Antarctica, and Australia. The richest dinosaur-bearing formations from this time come from Argentina and Brazil, with additional material from South Africa and Madagascar. Northern continents, which would become North America, Europe, and Asia, have yielded fewer and more fragmentary dinosaur fossils from the late Triassic. This geographic disparity may reflect genuine differences in dinosaur abundance, perhaps. Conditions in southern Pangaea were more favorable for early dinosaur diversification, or it may simply be an artifact of preservation, with better exposure of late Triassic rocks in South America providing more opportunities for discovery. By the Rhaetian stage, the final interval of the Triassic spanning from approximately 208 to 201 million years ago, dinosaur diversity had reached perhaps a dozen distinct genera across the three main lineages: theropods, prosauropods, and early ornithischians. They ranged in size from 1 meter to over 10 meters in length. They occupied ecological roles as small predators, mid-sized omnivores, and large herbivores. But they still shared their world with a far greater diversity of pseudosuchians, along with early mammals, various reptilian groups, and the first pterosaurs taking to the skies. The Triassic world was not a dinosaur world. It was an archosaur world, one in which multiple lineages coexisted in a complex web of competition and coexistence. That balance was about to be shattered in a way that no one group could have predicted or survived through superiority alone. The transition from the Triassic to the Jurassic period, precisely dated to 201.4 million years ago, represents one of the 5 major mass extinctions in the Phanerozoic Eon, the last 541 million years of Earth's history. But unlike the asteroid impact that would later end the age of dinosaurs, this extinction unfolded through processes originating deep within the planet itself. As Pangaea continued its slow fragmentation, tectonic forces were pulling the supercontinent apart along a north-south axis, creating a rift that would eventually become the Atlantic Ocean. Beneath this zone of weakness, mantle plumes, massive upwellings of superheated rock from deep within Earth's interior, were rising toward the surface. When they reached the crust, the result was volcanic activity on a scale difficult to comprehend. The Central Atlantic Magmatic Province, known by its acronym CAMP, began its main eruptive phase around 201 million years ago. CAMP was not a single volcano or even a volcanic field in the conventional sense. It was a large igneous province, a geological term for events where vast quantities of basaltic magma erupt through fissures in the Earth's crust across enormous geographic areas. The eruptions occurred along what would become the margins of 4 continents: eastern North America, northwestern Africa, northeastern South America, and southwestern Europe. Fissures hundreds of kilometers long opened in the crust, and basaltic lava poured out, flooding river valleys, burying forests, and coating the landscape in flows that could extend for hundreds of kilometers. Individual lava flows reached thicknesses of 100 meters or more. The total volume of magma emplaced is estimated at 2 to 3 million cubic kilometers, enough to bury the entire contiguous United States under a layer of rock approximately 600 meters thick. The eruptions were not continuous but occurred in pulses over approximately 600,000 years, with the most intense activity concentrated in the first 40,000 years, the geological instant. During this time, the environmental consequences cascaded through Earth systems with devastating efficiency. Volcanic eruptions release more than just lava. They emit gases, particularly carbon dioxide and sulfur dioxide. The camp eruptions injected an estimated 100,000 gigatons of carbon dioxide into the atmosphere. To put this in perspective, pre-industrial atmospheric CO2 levels were approximately 280 parts per million. The camp eruptions drove concentrations upward by potentially 2,000 parts per million or more. Global temperatures responded rapidly, increasing by 10 to 15 degrees Celsius above pre-eruption baselines within a few thousand years, an extreme and abrupt warming event. The oceans, which cover 71% of Earth's surface and act as a massive reservoir for atmospheric gases, absorb much of this carbon dioxide. When CO2 dissolves in seawater, it forms carbonic acid, lowering the pH of this water, a process called ocean acidification. For marine organisms that build shells or skeletons from calcium carbonate, acidified water is chemically hostile. The carbonate ions they need to construct their shells become less available, and in extreme cases, existing shells begin to dissolve. Corals, which build reefs from aragonite, a form of calcium carbonate, were devastated. Approximately 96% of coral genera disappeared, and reef ecosystems, which had existed continuously since the Triassic began, collapsed entirely. The fossil record shows what paleontologists call a coral gap in the early Jurassic, an interval where reefs are virtually absent from the geological record, indicating it took millions of years for reef ecosystems to recover. Bivalves, clams, and their relatives suffered heavy but selective losses. Some groups vanished entirely, while others persisted through the crisis. Ammonoids, the coiled-shelled cephalopods that had been extraordinarily diverse throughout the Triassic, were nearly wiped out. Only a single lineage, the Velociraptors, survived the boundary, and from this bottleneck, all Jurassic and Cretaceous ammonoids would later evolve. Conodonts, eel-like vertebrates with elaborate tooth structures that had existed for over 300 million years and served as critical index fossils for dating Paleozoic and Triassic rocks, became completely extinct. Their disappearance marks the Triassic-Jurassic boundary in marine sediments with stark clarity. Rocks below the boundary contain conodonts, rocks above do not. But the marine extinctions, severe as they were, represented only half the story. On land, the consequences were equally transformative. The warming climate, combined with changes in precipitation patterns driven by altered atmospheric circulation, restructured terrestrial ecosystems. Vegetation communities underwent radical shifts. Palynological studies, analyses of fossil pollen and spores, show abrupt changes in the composition of plant assemblages across the boundary. Species that had dominated late Triassic forests disappeared or became rare, replaced by opportunistic ferns and other early successional plants. This pattern, sometimes called a fern spike, appears in multiple locations globally and indicates ecological collapse followed by gradual recovery. The terrestrial vertebrate fauna experienced losses that were both profound and selective. Dinosaurs, the crocodile-like predators that had dominated rivers and lake margins throughout the late Triassic, vanished entirely. Not a single lineage survived into the Jurassic. Aetosaur, the heavily armored herbivores that had diversified into numerous species occupying roles similar to modern herbivorous mammals, disappeared. Rauisuchians, the apex predators of the late Triassic with their massive skulls and powerful limbs, were completely eliminated. In total, all archosauromorph reptiles except 3 groups, crocodilomorphs, dinosaurs, and pterosaurs, became extinct. The Pseudosuchian dynasty that had ruled terrestrial ecosystems for 30 million years ended not through competitive displacement, but through environmental catastrophe. The mechanisms behind these selective extinctions remain an active area of research, but the evidence points to multiple interacting stressors rather than a single catastrophic blow. The volcanic gases released by camp included not only carbon dioxide but also sulfur dioxide, which reacts with atmospheric moisture to form sulfuric acid, primary component of acid rain. Deposits from the Triassic-Jurassic boundary show elevated concentrations of mercury, a toxic element released during volcanic eruptions. Mercury levels in sedimentary rocks from sites in Europe, North America, and Asia spiked dramatically at the boundary layer, with concentrations sometimes reaching hundreds of parts per billion, levels far above natural background. This mercury would have contaminated food chains, accumulating in the tissues of organisms and potentially causing neurological damage, reproductive failure, and death. The carbon isotope record provides additional insights into the severity of the crisis. Carbon exists in two stable isotopes, carbon-12 and carbon-13. Living organisms preferentially incorporate the lighter carbon-12 into their tissues, so when massive amounts of organic carbon are oxidized, whether through volcanic heating of coal deposits or widespread die-off of vegetation, the atmosphere becomes enriched in isotopically light carbon. This shift is recorded in both marine carbonates and terrestrial organic matter across the Triassic-Jurassic boundary. Multiple negative carbon isotope excursions appear in the geological record, indicating repeated pulses of carbon release into the atmosphere over several 100,000 years. Each excursion corresponds to a phase of environmental deterioration, suggesting the extinction was not a single event but a series of cascading crises. In terrestrial ecosystems, the collapse of plant communities had cascading effects up the food chain. Herbivores that depended on specific plant types faced starvation, as those plants disappeared or became rare. Pollen records from the Newark supergroup in eastern North America show that approximately 60 of plant genera disappeared across the boundary, replaced initially by ferns and other opportunistic colonizers, species adapted for rapid growth in disturbed environments. This fern spike appears globally from Europe to Asia to the Americas, indicating that forests were replaced by low-diversity, pioneering vegetation similar to what appears after modern volcanic eruptions or forest fires. The terrestrial vertebrate groups that vanished, Phytosaurs, Aetosaur, and Rauisuchians, shared certain characteristics that may have made them vulnerable. Many were large-bodied, requiring substantial food resources to maintain their metabolism. As plant communities collapsed and herbivore populations crashed, the energy base supporting these large predators and herbivores disintegrated. Additionally, many pseudosuchians were likely ectothermic or had metabolic rates intermediate between modern reptiles and mammals, meaning their body temperatures and activity levels were influenced by external environmental temperatures. In a world experiencing rapid temperature swings, perhaps hot during the day due to greenhouse warming but experiencing extreme variability due to volcanic aerosols blocking sunlight, maintaining stable body temperature and activity patterns would have been challenging. Dinosaurs, by contrast, may have possessed physiological advantages that proved decisive during the crisis. While debates continue about dinosaur metabolism, evidence suggests many dinosaurs had elevated metabolic rates compared to typical reptiles, possibly approaching or even matching those of modern mammals in some lineages. Bone histology, microscopic analysis of bone structure, shows that dinosaurs laid down bone tissue rapidly, a feature associated with high growth rates and elevated metabolism. Their upright limb postures reduced energy expenditure during locomotion, and their respiratory systems, potentially featuring air sacs similar to modern birds, would have increased oxygen extraction efficiency. These features may have allowed dinosaurs to remain active and maintain energy balance during a time when resources were scarce and environmental conditions fluctuated wildly. Crocodilomorphs, the other pseudosuchian group that survived, possessed different but equally effective adaptations. They were primarily aquatic or semi-aquatic, occupying freshwater environments that were buffered against some of the worst effects of terrestrial climate change. Aquatic ecosystems, fed by rivers that continued to flow despite terrestrial vegetation collapse, maintain food chains based on detritus and aquatic insects. Crocodilomorphs were also capable of extended periods of inactivity, surviving on minimal food during lean times, a strategy still employed by modern crocodilians. Pterosaurs, the flying reptiles, likely survived due to their mobility, ability to exploit diverse food sources across wide geographic ranges, and relatively small body sizes in most late Triassic forms, which reduced absolute food requirements. The extinction did not occur uniformly across the planet. Some regions experienced more severe impacts than others, likely due to local environmental conditions and proximity to volcanic activity. Marine environments near the equator, where temperatures were already high, may have experienced lethal temperature spikes. High-latitude regions, where temperatures were cooler, may have served as refugia, safe havens where conditions remained tolerable. The fossil record shows evidence of geographic range shifts, with some species moving toward the poles to escape equatorial heat, only to face seasonal extremes and limited food resources at higher latitudes. By the time the eruptions ceased and atmospheric conditions began to stabilize in the early Jurassic, the world had been fundamentally reorganized. Approximately 76 of species were gone. The ecological roles they had occupied, apex predators, large herbivores, dominant plant species, were now vacant. And in this devastated world, dinosaurs faced less competition than they had in over 30 million years. The Pseudotsuchian rivals that had kept them marginalized were eliminated. The door to ecological dominance stood open, and dinosaurs, through a combination of anatomical advantage and sheer survival, were positioned to walk through it. The aftermath of the Triassic-Jurassic extinction reveals a pattern more complex than simple competitive replacement. When paleontologists analyzed the fossil record quantitatively, measuring not just which species existed but how morphologically diverse they were and how abundant they became, a surprising picture emerges. Dinosaur morphological disparity, the variety of body plans and anatomical configurations, did not experience a dramatic expansion immediately after the extinction event. The major jump in dinosaur disparity had already occurred earlier, between the Carnian and Norian stages of the late Triassic, when the fundamental dinosaur body plans, theropods, prosauropods, early sauropods, and ornithischians, first appeared and differentiated from one another. Across the Triassic-Jurassic boundary itself, morphological disparity showed only a slight, statistically non-significant increase. This finding contradicts what might be expected under a simple ecological release hypothesis, where the elimination of competitors should trigger an explosion of new body forms as survivors radiate into vacant niches. Yet the data show that dinosaurs did not substantially expand their morphospace in the early Jurassic despite the near-total extinction of Pseudotsuchian competitors that had been significantly more morphologically diverse. The implication is striking. The basic anatomical toolkit of dinosaurs was already established before their competitors disappeared. What changed was not what dinosaurs could do, but how many of them were doing it and where. Taxonomic diversity and faunal abundance tell a different story. While morphological disparity plateaued, the number of dinosaur genera increased steadily from the Carnian through the Norian and into the early Jurassic. Observed fossil occurrences show 9 dinosaur genera in the Carnian, 22 in the Norian, and 26 to 27 in the early Jurassic. When ghost lineages, evolutionary branches that must have existed based on phylogenetic relationships, even if fossils have not yet been found, are included, the total diversity rises from 23 genera in the Carnian to 31 in the Norian and 34 to 40 in the early Jurassic. Quantitative analyses of lineage diversification identify the early Jurassic as the single most important period for the origin of new dinosaur lineages, the time when the evolutionary tree underwent its most rapid branching. Equally important was the shift in faunal abundance, the proportion of individuals that were dinosaurs rather than other vertebrates. In late Triassic formations, dinosaur representation varies dramatically by location and latitude, comprising anywhere from less than 5 to perhaps 30 of large vertebrate fossils depending on the site. But in early Jurassic formations worldwide, dinosaurs consistently dominate the assemblages, often representing 80 or more of large terrestrial vertebrate specimens. This pattern holds across continents and climate zones, from the Kayenta Formation in North America to the Lufeng Formation in China to the Hansen Formation in Antarctica. By the early Jurassic, approximately 200 to 190 million years ago, dinosaurs had become the preeminent terrestrial vertebrates globally. The other surviving archosaur groups did not disappear, but found their own paths. Crocodilomorphs, the Pseudotsuchian lineage that would eventually give rise to modern crocodilians, underwent an extensive and rapid radiation during the early Jurassic. Interestingly, they occupied different regions of morphological space than their late Triassic Pseudotsuchian relatives had, suggesting they were exploiting different ecological niches rather than simply replacing the extinct forms. Early Jurassic crocodilomorphs exhibited remarkable diversity in lifestyle and diet. While modern crocodilians are largely confined to semi-aquatic ambush predation, their Jurassic ancestors included terrestrial forms with long legs built for running, herbivorous species with teeth adapted for grinding, plant material, and marine forms adapted for life in the open ocean. The first herbivorous crocodilomorph appears in the early Jurassic of Arizona, representing an ecological strategy that would appear multiple times during the Mesozoic. The early Jurassic world was warmer and more humid than the late Triassic. As Pangaea continued to fragment, ocean basins widened and sea levels rose, creating extensive shallow seas that moderated continental climates. The breakup of the supercontinent reduced the extreme continentality that had characterized the Triassic, bringing more consistent moisture to previously arid interior regions. Vegetation communities recovered from the end-Triassic collapse, with conifers, cycads, and ferns forming forests that were more extensive and productive than those of the late Triassic. This vegetative recovery provided the resource base that supported larger populations of herbivorous dinosaurs, which in turn supported growing populations of predators. The stage was set for the next phase of dinosaur evolution, the emergence of true giants and the establishment of complex, dinosaur-dominated ecosystems that would persist for another 135 million years. The early Jurassic, spanning from 201 to 174 million years ago, opened on a world still recovering from catastrophe. The volcanic eruptions had ceased, atmospheric carbon dioxide levels were gradually declining from their peak, and global temperatures, while still elevated compared to pre-extinction baselines, had stabilized. Pangaea continued its fragmentation, with the Proto-Atlantic Ocean slowly widening as North America separated from Africa and South America. This continental rifting had profound effects on climate patterns. The breakup of the supercontinent allowed ocean currents to penetrate regions that had previously been isolated, bringing moisture to continental interiors that had been scorched deserts during the Triassic. Sea levels rose as mid-ocean ridges formed and displaced water, flooding low-lying coastal areas and creating extensive shallow seas that acted as thermal buffers, moderating temperature extremes. The climate of the early Jurassic was warm and humid, with reduced seasonality compared to the extreme monsoon-driven patterns of the late Triassic. There is no evidence of polar ice caps. Even high-latitude regions experience temperate conditions. Fossil wood from Antarctica shows growth rings indicating seasonal variation, but the presence of forests at such latitudes demonstrates that temperatures remained above freezing year-round. Atmospheric circulation patterns shifted as Pangaea fragmented, reducing the intensity of continental monsoons and distributing precipitation more evenly across the year. This climatic moderation supported the expansion of vegetation communities that had been restricted during the harsher Triassic conditions. Plant communities underwent significant recovery and diversification. The fern spike that characterized the immediate post-extinction interval, a period dominated by opportunistic fern species colonizing disturbed landscapes, gradually gave way to more complex forest ecosystems. Conifers, which had survived the extinction in reduced numbers, expanded their range and diversity. Families like Araucariaceae and Podocarpaceae, which include modern relatives such as the monkey puzzle tree and yellowwood, became dominant components of early Jurassic forests. Cycads and cycadioids, palm-like plants with stout trunks and crowns of compound leaves, proliferated in tropical and subtropical regions. Ginkgos, represented today by a single species, were diverse and widespread. Ferns remained abundant in the understory, and horsetails grew along riverbanks and in wetlands. This vegetative recovery was essential for the expansion of herbivorous dinosaurs, which required enormous quantities of plant material to sustain their metabolism and growth. The three major dinosaur lineages, theropods, sauropodomorphs, and ornithischians, each responded to the post-extinction world in different ways, exploiting different resources and occupying distinct ecological roles. The early Jurassic witnessed the establishment of dinosaur-dominated ecosystems that would persist, with modifications, for the next 135 million years. Theropods, the bipedal carnivorous dinosaurs, diversified into a range of body sizes and hunting strategies. Small theropods, descendants of late Triassic forms, continued as agile predators of lizards, early mammals, and insects. Coelophysis, known from hundreds of skeletons at Ghost Ranch in New Mexico, dating to the very end of the Triassic and earliest Jurassic, exemplifies these small predators. Adults reached lengths of 3 meters and weighed approximately 15 to 30 kilograms, roughly the size of a large dog. Their skeletons were lightly built, with hollow bones that reduced weight, long legs suited for running, and grasping hands with sharp claws. Teeth were blade-like and serrated, ideal for slicing flesh. Some mass accumulation sites, where numerous individuals died together, have been interpreted as evidence of gregarious behavior, though whether these represent social groups or simply individuals attracted to a common resource like water during drought remains debated. Larger theropods also appeared, filling the apex predator role left vacant by the extinction of Rauisuchians. Dilophosaurus, from the early Jurassic Kayenta Formation of Arizona dating to approximately 193 million years ago, reached lengths of 6 to 7 meters and weighed an estimated 400 kilograms. It possessed a distinctive pair of thin, parallel crests running along the top of its skull, likely used for display rather than combat, as they were too fragile to withstand physical impact. The arms were relatively long and powerful, tipped with four-fingered hands bearing large claws, suggesting it used its forelimbs to grasp and manipulate prey. The jaws were robust, but analysis of the skull structure indicates the bite force was relatively weak compared to later large theropods, leading some paleontologists to propose that Dilophosaurus may have used its claws to kill prey and its jaws primarily for feeding rather than delivering fatal bites. But the most dramatic evolutionary developments of the early Jurassic occurred not among predators but among herbivores. The sauropodomorphs, which had appeared in the late Triassic as modest-sized prosauropods capable of both bipedal and quadrupedal locomotion, began a transformation that would culminate in the largest land animals ever to exist. This transition involved fundamental changes in body plan, feeding strategy, and ecology, changes that would define an entire branch of the dinosaur family tree for the duration of the Mesozoic era. The transition from prosauropods to true sauropods represents one of the most significant evolutionary transformations in vertebrate history. Prosauropods like Plateosaurus were facultatively quadrupedal, meaning they could walk on either 2 legs or 4, depending on circumstances. Their forelimbs were relatively short, their necks were moderately elongated, and their maximum body mass topped out around 4,000 kilograms. True sauropods, by contrast, were obligately quadrupedal. Their body plan made bipedal locomotion impossible. Their forelimbs lengthened dramatically, becoming roughly equal in length to the hind limbs, creating a columnar stance similar to modern elephants, but on a far larger scale. Their necks elongated substantially, in some species comprising more than half the total body length. And their body masses reached scales unprecedented in terrestrial animals, 20, 30, even 80 tons in later forms. This transformation began in the late Triassic and early Jurassic with transitional forms that bridged the gap between prosauropods and true sauropods. Fossils from the early Jurassic of South Africa and China preserve sauropodomorphs showing intermediate characteristics, longer necks than prosauropods but not yet reaching extreme proportions, forelimbs that were lengthening but still shorter than hind limbs, and body sizes that were increasing but had not yet reached gigantic scales. By the end of the early Jurassic, approximately 174 million years ago, true sauropods had appeared and were beginning their diversification into the major groups that would dominate the middle and late Jurassic. The selective pressures driving this evolution toward gigantism remain debated, but several factors likely contributed. The warm, humid climate of the Jurassic supported extensive forests of conifers, cycads, and other gymnosperms, plants that produce seeds without flowers. These plants were abundant but not necessarily nutritious. Their tissues contained high proportions of structural compounds like cellulose and lignin that are difficult to digest. Large body size conferred several advantages in this environment. First, larger animals have lower mass-specific metabolic rates. They require less food per kilogram of body weight than smaller animals. Second, larger animals have longer digestive tracts, providing more time for microbial fermentation to break down tough plant material. Third, height allowed access to vegetation beyond the reach of competitors, particularly the foliage and the canopy of tall conifer trees. The anatomical innovations that made extreme sauropod body sizes possible were numerous and interconnected. The most obvious was the elongated neck, which functioned as a mobile feeding apparatus, allowing sauropods to sweep through large volumes of vegetation without moving their massive bodies. The vertebrae forming these necks were extensively pneumatized, hollowed out by air-filled spaces that reduced weight while maintaining strength, similar to the pneumatic bones of modern birds. Some sauropod neck vertebrae were 90 air by volume, creating structures that were simultaneously enormous and relatively lightweight. The skull became progressively smaller and lighter, reducing the weight at the end of the neck lever. Teeth simplified into peg-like or pencil-like structures suited for stripping vegetation rather than chewing it. Sauropods swallowed plant material whole and processed it in the gut rather than in the mouth. The limbs evolved into straight, pillar-like columns optimized for supporting enormous weight. Unlike mammals, which typically have flexed limbs with bent knees and elbows, sauropods had nearly straight legs that transmitted weight directly downward through the bones to the ground, minimizing the muscular effort required to remain standing. The feet were short and broad, with the heels raised off the ground in a semi-digitigrade posture, standing on the toes, which reduced the stress on foot bones. Some of the largest sauropods had feet that left footprints over a meter in diameter. The tail was long and muscular, serving as a counterbalance to the long neck and possibly as a defensive weapon. Some tails ended in whip-like sections that could have been used to strike predators. Ornithischian dinosaurs, the other major herbivorous lineage, remained less conspicuous during the early Jurassic but were diversifying in ways that would later prove significant. Early ornithischians were small, bipedal herbivores, but by the early Jurassic, some lineages were experimenting with armor. Celutosaurus, from the early Jurassic of England dating to approximately 191 million years ago, reached lengths of 4 meters and possessed rows of bony plates embedded in the skin along its back and sides, early armor that foreshadowed the heavily protected ankylosaurs and stegosaurs that would appear later. The presence of this armor suggests that predation pressure was sufficient to select for defensive adaptations, even in animals that were still relatively small by later Jurassic standards. By the end of the early Jurassic and into the middle Jurassic, dinosaur dominance was firmly established. They occupied every terrestrial ecological role from small insectivores to apex predators to massive herbivores. The stage was set for the Age of Giants, when sauropods would reach sizes that remain, even today, difficult to fully comprehend. The Jurassic was no longer a world recovering from catastrophe. It was a world rebuilt by dinosaurs. The Middle Jurassic, spanning from 174 to 163 million years ago, witnessed the continuation and acceleration of trends that had begun in the early Jurassic. Continental fragmentation proceeded steadily as Pangaea's breakup created new ocean basins and reshaped global climate patterns. Laurasia, the northern landmass comprising what would become North America, Europe, and Asia, began separating from Gondwana, the southern supercontinent. The Tethys Ocean, which had existed as an eastern embayment in Pangaea, expanded westward. New seaways opened between continents, flooding low-lying areas and creating extensive shallow marine environments. These epicontinental seas, shallow waters covering continental crust, became havens for marine life and acted as heat reservoirs that moderated coastal climates. Sea levels during the Middle Jurassic were among the highest of the entire Mesozoic era, with estimates suggesting they stood 100 to 200 meters above current levels. This transgression, the flooding of continental margins, created ideal conditions for the deposition of marine sediments that would later yield rich fossil deposits. The famous limestone formations of southern Germany, including the Solnhofen limestone dating to the late Jurassic, were deposited in shallow lagoons during this time of high sea levels. Similarly, marine deposits in England, France, and other European locations preserve abundant fossils from Middle and Late Jurassic seas. The marine realm underwent its own evolutionary expansion during this time. Plesiosaurs, long-necked marine reptiles that had survived the Triassic-Jurassic extinction, diversified into numerous families occupying different ecological niches. Some retain long necks and small heads, feeding on fish and squid in open water. Others, called pliosaurs, evolved short necks and massive heads exceeding 2 meters in length, becoming apex predators capable of hunting large prey, including other marine reptiles. Ichthyosaurs, dolphin-like reptiles that had appeared in the Triassic, continue to thrive, with some species reaching lengths of 15 meters or more. Marine crocodilomorphs adapted to fully aquatic lifestyles, developing streamlined bodies and paddle-like limbs. The seas were as dominated by reptiles as the land, creating ecosystems without modern parallel. On land, dinosaur faunas showed increasing provincial differentiation, regional differences in species composition, as continental separation created geographic barriers that isolated populations and allowed distinct evolutionary trajectories. The Morrison Formation of Western North America, dating to approximately 156 to 147 million years ago in the late Jurassic, preserves one of the most famous and thoroughly studied dinosaur assemblages. Its fauna included massive sauropods like Brachiosaurus, Diplodocus, Apatosaurus, and Camarasaurus, all coexisting in the same ecosystems. Theropod predators included Allosaurus, Ceratosaurus, and smaller forms like Ornitholestes. Ornithischian herbivores were represented by the plated Stegosaurus and the small bipedal Dryosaurus. This diversity of large-bodied animals, all living contemporaneously in the same region, indicates that late Jurassic ecosystems were extraordinarily productive, capable of supporting multiple species of multi-ton herbivores and the predators that hunted them. Similar assemblages existed on other continents. The Tindaguru beds of Tanzania, also late Jurassic in age, contain fossils of sauropods closely related to North American forms, indicating that despite continental separation, some degree of faunal interchange still occurred. Chinese dinosaur faunas from the Middle and Late Jurassic show both similarities and differences, with specialized theropods like Metriacanthosaurids and distinctive sauropods like Mamenchosaurus, which possessed one of the longest necks of any dinosaur, up to 15 meters in some estimates, comprising more than half its total body length. The vegetation supporting these ecosystems remained dominated by gymnosperms, non-flowering seed plants. Conifers formed the canopy of forests, reaching heights of 30 meters or more. Cycads and cycadioids provided mid-story vegetation. Ferns covered the forest floor and thrived in wet lowlands. Ginkgos were widespread. Tree ferns, which can still be found in tropical and subtropical regions today, added to the vertical complexity of forests. This plant diversity, combined with warm temperatures and high atmospheric carbon dioxide levels that enhanced photosynthetic productivity, created environments capable of producing the enormous quantities of biomass required to sustain populations of giant herbivores. The Middle to Late Jurassic represents the maturation of dinosaur-dominated ecosystems, complex, productive, and stable communities that would persist with modifications through the remainder of the Jurassic and into the Cretaceous. The stage was now fully set for the Age of Giants, when the largest land animals in Earth's history would stride across landscapes from North America to Africa to Asia, their footsteps shaking the ground and their bodies reshaping the very structure of the forests through which they moved. Between 174 and 145 million years ago, during the Middle and Late Jurassic, the Earth witnessed the emergence of the largest land animals that have ever existed. Sauropod dinosaurs reached sizes that challenge comprehension, animals weighing 30, 40, even 80 tons, with body lengths exceeding 30 meters and necks that could reach into forest canopies 15 meters above the ground. To put this in perspective, the largest land animal alive today, the African elephant, weighs approximately 6 tons at maximum, less than 1/10 the mass of the largest sauropods. Modern blue whales, the largest animals ever to exist, achieve greater masses than the largest sauropods, but they live in water, which supports their weight through buoyancy. Sauropods achieve their massive sizes while walking on land, supporting their entire body weight on 4 columnar legs, breathing air, and maintaining the metabolic processes necessary for life. Brachiosaurus, discovered in the Morrison Formation of Colorado, and dating to approximately 154 to 150 million years ago, exemplifies the gigantism of late Jurassic sauropods. Adults reached lengths of 18 to 21 meters and heights of 9 to 13 meters, with mass estimates ranging from 28 to 58 tons depending on the reconstruction method used. Unlike many sauropods, which had relatively level backs, Brachiosaurus possessed forelimbs that were longer than its hind limbs, creating a giraffe-like posture with the shoulders elevated above the hips. This body plan meant the neck, already long at approximately 9 meters, was angled upward from an already elevated base, allowing the head to reach extraordinary heights. The skull was small and delicate, weighing perhaps 100 kilograms, with large nasal openings positioned high on the head, once thought to indicate an aquatic lifestyle, but now understood to be related to thermoregulation or enhanced olfaction. Diplodocus, another Morrison Formation giant, demonstrated a different approach to extreme size. At lengths reaching 25 to 30 meters, it was among the longest dinosaurs, but much of this length came from an extraordinarily long tail that may have contained over 80 vertebrae, more than any other known dinosaur. The tail was whip-like at its end, tapering to a thin, flexible tip that some researchers believe could have been cracked like a bullwhip, producing a loud sound for communication or intimidation. Computer modeling of tail biomechanics suggests the tip could have achieved supersonic speeds, creating a sonic boom. Mass estimates for Diplodocus range from 10 to 16 tons, large by any standard, but lighter than Brachiosaurus due to a more slender build and especially elongated vertebrae that were extensively pneumatized. Apatosaurus, formerly known by the now invalid name Brontosaurus, though recent research suggests Brontosaurus may be a valid genus after all, was a more robustly built sauropod from the same Morrison Formation ecosystems. Adults reached lengths of 21 to 23 meters and masses estimated at 16 to 22 tons, with some individuals possibly exceeding 30 tons. The neck was thick and muscular, suggesting it could exert substantial force, useful for pushing through vegetation or possibly in intraspecific combat, where males might have used their necks as weapons against rivals. Fossilized trackways show that sauropods typically moved at walking speeds of 2 to 4 kilometers per hour, though they were capable of faster movement when necessary. These giants shared the late Jurassic landscape, coexisting in the same time and place, raising an obvious question: how could multiple species of enormous herbivores, each requiring massive quantities of food, live together without depleting resources or outcompeting one another to extinction? The answer lies in niche partitioning, different species exploiting different resources. Evidence suggests that sauropod species fed at different heights and on different plant types. Brachiosaurus, with its upward-angled neck and high shoulder, was a high browser, feeding on foliage in the upper canopy of conifer trees beyond the reach of other herbivores. Diplodocus, with its long but horizontally oriented neck, was likely a ground-level or low browser, sweeping its neck from side to strip vegetation from a wide area without moving its body. Camarasaurus, another Morrison Formation sauropod, had a shorter, more robust skull with large, spoon-shaped teeth capable of processing tougher vegetation that other sauropods might have avoided. Tooth morphology varied significantly among sauropod species, reflecting dietary specialization. Diplodocus and its relatives possessed pencil-like teeth arranged only at the front of the jaws, an adaptation for stripping leaves from branches but not for chewing. These dinosaurs swallowed vegetation whole and processed it in the gut through microbial fermentation and possibly with the aid of gastroliths, smooth stones deliberately swallowed that acted as a grinding mill in the stomach, similar to a bird's gizzard. Camarasaurus, by contrast, had broader, more robust teeth throughout the jaw, suggesting it could crop tougher, woodier vegetation. Brachiosaurus had chisel-like teeth, a middle ground between the two extremes. The Morrison Formation, extending across what is now Colorado, Wyoming, Utah, and neighboring states, preserves one of the most complete windows into late Jurassic ecosystems. Deposited between 156 and 147 million years ago, it represents an environment of river systems, floodplains, and seasonal wetlands in a semi-arid to subhumid climate. Conifers dominated the vegetation, with ferns, cycads, and tree ferns providing additional plant diversity. The abundance of sauropod fossils, often representing 70 or more of dinosaur specimens in Morrison sites, indicates these giants were not rare oddities but dominant members of the ecosystem, present in large numbers. The physics of supporting 30 to 80 tons on land presents extraordinary engineering challenges. Modern elephants, at 6 tons, already experience significant stress on their skeletal systems, and scaling up body mass causes problems that increase exponentially. When an animal doubles in linear dimensions, its mass increases by a factor of 8 length times width times height, but the cross-sectional area of its bones only increases by a factor of 4 length times width. This means larger animals experience disproportionately greater stress on their skeletons, a principle known as allometric scaling. Yet sauropods achieved masses 10 times greater than elephants while remaining mobile and active throughout their lives. The solution lay in a combination of anatomical innovations that reduced weight while maintaining structural integrity. Pneumatization, the presence of air-filled spaces within bones, was perhaps the most important weight-saving adaptation. In sauropod vertebrae, these pneumatic spaces were created by extensions of the respiratory system called air sacs, similar to those found in modern birds. CT scans of fossilized sauropod vertebrae reveal complex internal architectures with thin bony struts arranged in patterns that maximize strength while minimizing mass. Some vertebrae were up to 90 air by volume, reducing the weight of the vertebral column by half or more compared to solid bone. The long bones of the limbs were also hollowed, though to a lesser degree than the vertebrae, creating structures that function like hollow steel tubes, strong in compression and bending while using minimal material. The respiratory system itself was likely highly efficient. Modern birds possess a flow-through respiratory system where air moves in one direction through the lungs, with air sacs acting as bellows that keep fresh air constantly flowing. This system is far more efficient than the tidal breathing of mammals, where air moves in and out of the lungs, meaning that not all the air is refreshed with each breath. Evidence strongly suggests that sauropods possessed a similar flow-through system. The presence of pneumatic bones indicates air sacs, and the arrangement of openings in the vertebrae suggests these sacs extended throughout the body cavity and into the neck. This respiratory efficiency would have been crucial for supporting the high metabolic demands of such enormous bodies. Growth rates provide additional insights into sauropod biology. Analysis of bone histology, microscopic examination of thin sections of fossil bone, reveals growth patterns preserved in the bone tissue itself. Like tree rings, dinosaur bones show lines of arrested growth, lags, that mark periods when growth slowed or stopped, typically during seasonal resource scarcity. By counting these lines and measuring the spacing between them, paleontologists can reconstruct growth curves. Studies of sauropod bones show that these animals grew extraordinarily rapidly during their juvenile and subadult years. A sauropod might hatch from an egg weighing a few kilograms and reach sexual maturity at 10 to 20 tons within 15 to 20 years, growth rates exceeding 2 tons per year during peak growth phases. This rapid growth required enormous food intake and supports the hypothesis that sauropods had elevated metabolic rates compared to typical reptiles. The Morrison Formation provides a remarkable snapshot of how these giants lived. Fossilized trackways show sauropods moving in groups, with parallel sets of footprints suggesting coordinated movement, possible evidence of herding behavior. Some trackway sites preserve prints from individuals of different sizes walking together, which may indicate mixed-age groups or family units traveling as cohesive social groups. One site in Colorado preserves a trackway of a large sauropod paralleled by smaller prints, interpreted by some paleontologists as an adult accompanied by juveniles, though this interpretation remains speculative. Mass mortality assemblages, where multiple individuals died together, occur at several Morrison sites and may represent drought-related deaths at water sources or catastrophic flooding events that trapped herds. The predators that hunted in Morrison Formation ecosystems faced formidable prey. Allosaurus fragilis, the most common large theropod in the Morrison, reached lengths of 8 to 10 meters and masses of 1 to 2 tons, large and powerful, but still only a fraction of the size of adult sauropods. Evidence of sauropod-theropod interactions comes from bite marks on sauropod bones that match Allosaurus teeth, and from an Allosaurus skeleton found with injuries consistent with being struck by a sauropod tail. Whether Allosaurus hunted adult sauropods or focused on juveniles and sick individuals remains debated, but the presence of sauropod bones with theropod tooth marks indicates that Allosaurus at least scavenged sauropod carcasses, if not actively hunting them. The late Jurassic world of 150 million years ago was a planet at the peak of sauropod dominance, a time when the largest land animals in Earth's history walked beneath conifer forests, their footsteps shaking the ground, their immense bodies reshaping vegetation patterns, their populations sustained by ecosystems of extraordinary productivity. This was the age of giants, and it would continue with modifications for another 80 million years. The late Jurassic sauropod faunas were not restricted to North America. Comparable assemblages existed on other continents, demonstrating that gigantism was a global phenomenon rather than a regional anomaly. The Tendaguru Formation in Tanzania, dating to approximately 150 to 145 million years ago, preserves one of the richest dinosaur assemblages outside North America. Discovered in the early 20th century and extensively excavated by German paleontologists, Tendaguru has yielded enormous quantities of sauropod material, including specimens of Giraffatidan, closely related to, and possibly synonymous with Brachiosaurus, Dicryosaurus, and Tornaria. The similarity between North American and African sauropod faunas suggests that despite continental separation, land connections or island chains allowed faunal interchange between Laurasia and Gondwana during the late Jurassic. The Lourinhã Formation of Portugal, also late Jurassic in age, contains yet another diverse dinosaur fauna including sauropods, theropods, and ornithischians. Portuguese sauropods show affinities with both North American and African forms, consistent with Portugal's paleogeographic position on the eastern margin of the opening Atlantic Ocean. This European fauna demonstrates that sauropods had achieved nearly global distribution by the late Jurassic, with populations thriving from the Americas to Africa to Europe and Asia. Chinese late Jurassic formations preserve sauropods with distinctive characteristics that set them apart from their Western counterparts. Mamenchosaurus, from the Shaximio Formation of Sichuan Province dating to approximately 160 million years ago, possessed a neck of extraordinary length, up to 15 meters in some species, comprising more than half the animal's total body length of 25 meters. The neck contained 19 cervical vertebrae, more than any other known sauropod, creating a structure of remarkable reach. Whether Mamenchosaurus could hold this neck in a fully upright posture or was restricted to more horizontal orientations remains debated, as the biomechanics of supporting such an extreme structure present formidable challenges. The climate and vegetation of the late Jurassic provided ideal conditions for sustaining large populations of giant herbivores. Global temperatures were warm, with mean annual temperatures estimated at 3 to 10 degrees Celsius above modern values. There were no polar ice caps, and even high-latitude regions experienced temperate conditions that supported forest growth. Atmospheric carbon dioxide levels, while declining from their Triassic-Jurassic boundary peak, remained elevated compared to pre-industrial modern levels, likely in the range of 1,000 to 2,000 parts per million. These elevated CO2 concentrations would have enhanced plant photosynthesis and growth rates, increasing primary productivity, the total biomass produced by vegetation, and creating abundant food resources for herbivores. The Morrison Formation environment, reconstructed from sedimentology and paleobotany, was characterized by seasonal rainfall with wet and dry periods. Rivers meandered across broad floodplains, creating a mosaic of habitats including riparian forests along watercourses, more open woodland in better drained areas, and fern-dominated lowlands in poorly drained regions. The vegetation was dominated by conifers that could reach substantial heights, providing vertical structure to forests and creating the canopy layers that high-browsing sauropods exploited. This environmental complexity supported not just sauropods but an entire ecosystem of herbivores, predators, and smaller vertebrates and invertebrates. The Age of Giants represents a unique period in Earth's history when the interplay of favorable climate, productive vegetation, and evolutionary innovation produced land animals of unprecedented size. These creatures were not evolutionary dead ends or biological curiosities. They were successful, diverse, and ecologically dominant for tens of millions of years. The sauropod body plan proved remarkably durable, persisting through the remainder of the Jurassic and throughout the Cretaceous period until the final extinction 66 million years ago. While individual species came and went, and body sizes fluctuated in response to changing conditions, the fundamental success of gigantism as a survival strategy remained unquestionable. The late Jurassic was their zenith, the time when the largest of the giants walked the earth, and the world, for a geological moment, belonged to them. The Jurassic world of giant herbivores required equally impressive predators to maintain ecological balance. While sauropods dominated the landscape in terms of sheer biomass, theropod dinosaurs, the bipedal carnivores, occupied every predatory niche from small insect eaters to apex hunters capable of taking down multi-ton prey. The late Jurassic, in particular, witnessed the emergence of some of the most formidable predators of the Mesozoic era, animals whose fossilized remains reveal sophisticated hunting adaptations, complex behaviors, and ecological strategies that allowed them to thrive in ecosystems dominated by giants. Allosaurus fragilis stands as the quintessential Jurassic predator. Known from dozens of specimens recovered from the Morrison Formation of the western United States, dating to approximately 155 to 145 million years ago, Allosaurus was the most common large predator in late Jurassic North America. Adults reached lengths of 8 to 10 meters from snout to tail tip, stood approximately 3 meters tall at the hip, and weighed between 1,000 and 2,000 kilograms, roughly the mass of a large automobile. This placed Allosaurus firmly in the upper tier of predators, large enough to pose a threat to most prey animals in its ecosystem, yet still dwarfed by the largest sauropods. The skull of Allosaurus reveals a predator designed for power and efficiency. At just over 90 centimeters in length, the skull was massive yet surprisingly lightweight, with large fenestrae, skull openings, that reduced weight while maintaining structural strength. The jaws were lined with blade-like teeth, each tooth serrated on both front and rear edges like a steak knife, creating cutting surfaces ideal for slicing through flesh. Unlike the conical teeth of modern crocodiles, which are designed to grip and hold prey, Allosaurus teeth were laterally compressed, thin from side to side, maximizing their cutting ability. Tooth replacement was continuous throughout life, with new teeth constantly growing to replace those lost or worn during feeding. Some Allosaurus specimens preserve dozens of replacement teeth in various stages of development. The jaw mechanics of Allosaurus have been extensively studied using biomechanical modeling and comparisons with modern predators. The jaw muscles attached to prominent crests on the skull, particularly the sagittal crest running along the top of the head, providing leverage for powerful biting. However, bite force estimates suggest that Allosaurus was not capable of delivering the bone-crushing bites of later tyrannosaurids. Instead, the skull appears optimized for a different hunting strategy. The head was used as a hatchet. Computer simulations show that Allosaurus could open its jaws extremely wide, up to 92 degrees, and use the entire skull as a weapon, driving the upper teeth downward into prey with tremendous force generated by powerful neck muscles. This hatchet attack would inflict deep, devastating wounds, causing massive blood loss and shock. The forelimbs of Allosaurus were short relative to body length but remarkably powerful. Each arm ended in a 3-fingered hand bearing large, curved claws up to 15 centimeters long. The shoulder girdle and arm bones show robust muscle attachment sites indicating powerful grasping ability. These arms were too short to reach the ground but were perfectly positioned to grab and hold struggling prey, while the jaws delivered killing bites. The combination of grasping forelimbs and specialized jaw mechanics made Allosaurus a formidable predator capable of tackling large, dangerous prey. Evidence of Allosaurus feeding behavior comes from multiple sources. Sauropod bones from Morrison Formation sites bear tooth marks that match Allosaurus dentition in size and spacing. Some bones show evidence of repeated biting, suggesting either prolonged feeding or multiple individuals feeding on the same carcass. At the Cleveland Lloyd Dinosaur Quarry in Utah, over 10,000 dinosaur bones have been excavated, with Allosaurus representing 46 of the 73 individual dinosaurs identified, an unusually high proportion of predators. Various hypotheses have been proposed to explain this concentration. A predator trap where herbivores became mired in mud and Allosaurus individuals, attempting to feed on trapped prey, also became trapped, a drought-related mass death at a water source, or a den site used repeatedly over time. Whatever the explanation, the site demonstrates that Allosaurus was abundant in Morrison Formation ecosystems. The question of whether Allosaurus hunted in packs or as a solitary predator remains contentious. Trackway evidence from Portugal preserves multiple large theropod footprints moving in the same direction, suggesting coordinated movement, though whether this represents cooperative hunting or simply multiple individuals using the same travel route is debatable. The Cleveland Lloyd assemblage could indicate social aggregation, though the concentration might equally result from individuals drawn independently to a common resource. Analysis of growth rates from bone histology shows that Allosaurus grew rapidly during juvenile stages, potentially reducing the period of vulnerability to other predators and competitors, a strategy that could work for either social or solitary hunters. Ceratosaurus nasicornis, another Morrison Formation predator contemporary with Allosaurus, offers insight into ecological partitioning among Jurassic theropods. Reaching lengths of 6 to 7 meters and masses of 500 to 1,000 kilograms, Ceratosaurus was smaller than Allosaurus, but distinguished by unique features including a prominent nasal horn, bony osteoderms, armor plates, running along the midline of the back, and unusually robust teeth. The nasal horn was likely used for display rather than combat, as it was too fragile to withstand impact. The teeth, however, suggest different feeding ecology than Allosaurus. They were more robust and less blade-like, possibly indicating a diet including tougher prey or more bone consumption. The presence of osteoderms is unusual among large theropods and suggests Ceratosaurus may have faced greater intraspecific competition or predation pressure than other large theropods. Smaller theropods filled different ecological niches in Morrison Formation ecosystems. Ornitholestes, known from a single, nearly complete skeleton from Wyoming, reached lengths of only 2 meters and weighed approximately 12 to 15 kilograms, roughly the size of a medium dog. The name means bird robber, reflecting early speculation that it hunted the primitive bird Archaeopteryx, but this interpretation is unlikely given the geographic and temporal separation between the two animals. More probable is that Ornitholestes hunted small vertebrates such as lizards, early mammals, and possibly insects. The hands were specialized with one greatly enlarged claw on each, suggesting grasping adaptations for catching small, agile prey. The skull was lightly built with small, pointed teeth suited for puncturing rather than slicing, consistent with a diet of small animals. The prey available to Jurassic predators extended far beyond sauropods. Ornithischian dinosaurs, though less diverse in the Jurassic than they would become in the Cretaceous, provided additional herbivore biomass. Stegosaurus, one of the most recognizable dinosaurs, reached lengths of 7 to 9 meters and masses of 3 to 5 tons. The distinctive double row of plates along the back has generated extensive debate regarding function. Early hypotheses suggested the plates serve as armor, but their thin structure and lack of overlap make this unlikely. They would have been easily broken by a determined predator. Alternative hypotheses include thermoregulation, with the plates serving as heat radiators or absorbers, and display, with the plates used for species recognition or intimidation. The tail of Stegosaurus ended in 4 long spikes called a thagomizer, a term coined by cartoonist Gary Larson, but now widely used by paleontologists that serve as weapons. Evidence of predator-prey interactions between Allosaurus and Stegosaurus comes from multiple fossil specimens. An Allosaurus vertebra found in Wyoming bears a circular puncture wound matching the size and shape of a Stegosaurus tail spike. The wound shows evidence of infection and partial healing, indicating the Allosaurus survived the injury, but was significantly weakened. Another Allosaurus specimen discovered in Colorado preserves multiple puncture wounds through the pelvis consistent with repeated strikes from stegosaur tail spikes. This individual did not survive. The extent of damage to the pelvis would have made locomotion impossible, and the animal likely died from infection or inability to hunt. These fossils provide rare direct evidence of predator-prey combat in the fossil record, demonstrating that Jurassic herbivores were far from defenseless and that hunting large prey carried significant risks even for apex predators. Camptosaurus, a medium-sized ornithopod herbivore, represented another prey option. Adults reached lengths of 5 to 7 meters and weighed between 500 and 1,000 kilograms. Unlike the quadrupedal Stegosaurus, Camptosaurus was primarily bipedal, capable of running on its hind legs to escape predators. The lack of obvious defensive weapons suggests speed was its primary defense strategy. Juvenile sauropods would have been vulnerable targets during their early growth stages before reaching sizes that made them relatively immune to predation. A hatchling sauropod emerging from an egg might weigh only a few kilograms and would remain vulnerable to predation for years until reaching adult size. The structure of Morrison Formation predator guilds, the suite of predators in an ecosystem, shows size stratification. Large predators like adult Allosaurus, 1 to 2 tons, occupied the apex predator niche. Medium predators like Ceratosaurus, 500 to 1,000 kilograms, and juvenile Allosaurus hunted mid-sized prey. Small predators like Ornitholestes, 10 to 15 kilograms, pursued small vertebrates and possibly insects. This size stratification reduced competition by partitioning prey resources according to predator body size, a pattern seen in modern ecosystems where lions, leopards, and jackals coexist by hunting different prey sizes. The late Jurassic represents the zenith of predator diversity before the emergence of tyrannosaurs in the Cretaceous. These Jurassic hunters, with their specialized adaptations and complex ecological relationships, maintained balance in ecosystems dominated by the largest herbivores ever to walk the Earth. For 10 million years, from approximately 155 to 145 million years ago, the Morrison Formation ecosystem functioned as a complex web of predators and prey, each species occupying its role in one of the most productive terrestrial ecosystems in Earth's history. The Morrison Formation ecosystem extended across approximately 1.5 million square kilometers of the western United States during the late Jurassic, creating a vast interconnected landscape that supported one of the most diverse dinosaur assemblages in Earth's history. The environment was not uniform, but rather a complex mosaic of habitats that shifted through time and space. Climate models and geological evidence indicate the region experienced a semi-arid climate, dry overall but with critical water sources that concentrated life in specific zones. The hydrology of the Morrison Basin was fundamental to understanding how such large populations of enormous animals could be sustained. Two primary water sources existed: groundwater that originated in the western uplands and recharged aquifers beneath the basin, and surface water from intermittent streams that flowed eastward from highlands to the west. These streams were likely losing streams in their upstream reaches, meaning they contributed water to the groundwater table rather than receiving it. Where the floodplain intersected the water table, small lakes and wetlands formed, creating oases in an otherwise dry landscape. Seasonal storms, possibly originating from the Paleogulf of Mexico, brought additional precipitation directly to the basin, though the amounts were limited. Riparian environments, the zones along rivers and streams, were the most diverse and productive parts of the ecosystem. These areas supported multi-storied vegetation canopies with tall conifers dominating the upper layers, cycads and tree ferns in the mid-story, and ferns and horsetails covering the ground. Fossil evidence from the Morrison Formation includes Brachyphyllum and Araucariaceae conifers that reached heights comparable to modern redwoods, creating forests that towered over even the largest sauropods. These riparian corridors functioned as linear oases stretching across the landscape, supporting diverse fauna from insects to dinosaurs. The large herbivorous dinosaurs were specifically adapted to the semi-arid landscape. Their enormous size, often viewed as a liability requiring massive food intake, was actually an adaptive advantage. Large body size correlated with low mass-specific metabolic rates, meaning sauropods required less food per kilogram of body weight than smaller animals. Additionally, their size made them capable of long-distance migration during drought periods. They could travel to distant water sources and riparian zones when local resources became scarce. Some sauropods were adapted to browsing the higher vegetation in riparian forests, while others grazed on herbaceous ground cover that appeared seasonally on the floodplain or consumed charophytes in wetlands. For predators like Allosaurus and Ceratosaurus, this ecosystem structure created both opportunities and challenges. The concentration of herbivore populations around water sources during dry periods would have created predictable hunting opportunities, similar to modern African predators waiting at waterholes during droughts. The riparian corridors served as travel routes and hunting grounds where predators could ambush prey, coming to drink or feed. However, the seasonal nature of resources meant predator populations had to be sufficiently mobile to follow prey movements across the landscape or capable of surviving extended periods with limited food. The Morrison Formation preserves evidence of at least 3 severe drought events followed by localized flooding when rains returned. These cycles of drought and flood would have dramatically impacted predator-prey dynamics. During droughts, weakened herbivores would have been easier prey, but overall prey abundance would decline. Flooding events could trap animals in mud or quicksand, creating mass mortality sites that attracted scavengers. The Cleveland Lloyd dinosaur quarry's unusual concentration of Allosaurus specimens may represent one such predator trap, where multiple individuals died while attempting to feed on trapped prey or were themselves caught in treacherous ground conditions. The Morrison ecosystem, likened by paleontologists to a savanna but dominated by gymnosperms rather than grasses, represented a complex, shifting mosaic of habitats that sustain the most spectacular assemblage of giant animals in terrestrial history. For predators, survival required not just hunting prowess, but also the ability to navigate seasonal resource fluctuations, exploit diverse prey options, and compete with other predators for access to kills. This was not a static environment, but a dynamic system where water availability dictated the distribution of life, and predators adapted their strategies to the rhythms of drought and rainfall that governed the late Jurassic world. The boundary between the Jurassic and Cretaceous periods, dated to 145 million years ago, marked no catastrophic extinction event, no volcanic eruptions, no asteroid impacts, no mass die-offs. Instead, the transition was gradual, characterized by slow but fundamental changes in Earth's geography, climate, and biology that would reshape the world and accelerate dinosaur evolution in entirely new directions. The supercontinent Pangaea, which had been fragmenting since the late Triassic, was now separating into distinct landmasses that would eventually become the modern continents. Laurasia, the northern supercontinent comprising North America, Europe, and Asia, was itself beginning to split apart. Gondwana, the southern landmass, was fracturing into South America, Africa, India, Antarctica, and Australia. New ocean basins widened, and seaways flooded low-lying areas, creating geographic barriers that isolated dinosaur populations and allowed independent evolutionary trajectories to unfold across different continents. The climate of the early Cretaceous, spanning from 145 to 100 million years ago, remained warm and generally free of polar ice, continuing trends established in the Jurassic. However, temperature patterns were shifting due to changing ocean circulation as new seaways opened. The Atlantic Ocean, which had begun forming during the Jurassic, continued to widen, allowing water to flow between continents that had been connected for hundreds of millions of years. This altered heat distribution around the globe, creating more moderate coastal climates in regions that had previously been continental interiors. Sea levels fluctuated but trended upward, with major transgressive episodes flooding continental margins and creating extensive shallow seas, epicontinental seas, that covered portions of what are now Europe, Central North America, and other regions. These shallow seas became havens for marine life and dramatically influenced terrestrial ecosystems along their margins. Coastal environments benefited from moderated temperatures and increased moisture, supporting lush vegetation that provided abundant resources for herbivorous dinosaurs. The fragmentation of landmasses created smaller, more isolated environments compared to the vast continuous landscapes of the Jurassic. On these smaller landmasses, dinosaur populations evolved in isolation from one another, leading to increased endemism, species unique to specific geographic regions. A dinosaur fauna in South America began to diverge from its African counterparts as the South Atlantic Ocean widened. Asian dinosaurs developed characteristics distinct from North American forms as the Turgos Strait periodically flooded the region between them. The dinosaur families that emerged during the early Cretaceous would come to define the latter half of the Mesozoic era. Among ornithischians, ceratopsians, the horned dinosaurs, appeared in the fossil record. Early forms like Psittacosaurus from China, dating to approximately 126 to 101 million years ago, were small bipedal herbivores reaching only 2 meters in length, with distinctive parrot-like beaks and simple bony frills at the back of the skull. These modest creatures bore little resemblance to the massive, heavily horned ceratopsians like Triceratops that would appear 70 million years later, yet they possessed the fundamental anatomical features that define the group: the rostral bone at the tip of the upper jaw forming a sharp beak, and the beginnings of the neck frill that would become so elaborate in later species. Ankylosaurs, the armored dinosaurs, also diversified during the early Cretaceous. While their Jurassic ancestors like Solidosaurus had possessed simple rows of bony plates, early Cretaceous ankylosaurs developed extensive body armor consisting of interlocking osteoderms that covered the back, sides, and even the eyelids. Sauropelta from the early Cretaceous of North America, dating to approximately 115 to 108 million years ago, reached lengths of 5 to 7 meters and weighed up to 1,500 kilograms. Its body was covered in thick armor plates, and rows of prominent spikes projected from its neck and shoulders, formidable defenses against the predators of its time. Among theropods, the early Cretaceous witnessed the emergence of new predatory lineages that would eventually replace the allosaurs and ceratosaurs of the Jurassic. Carcharodontosaurids, shark-toothed dinosaurs named for their blade-like teeth resembling those of the great white shark, appeared and quickly grew to enormous sizes. Acrocanthosaurus, from the early Cretaceous of North America dating to approximately 116 to 110 million years ago, reached lengths of 11 to 12 meters and masses exceeding 6 tons, making it larger than Allosaurus and one of the largest predators of its time. The most distinctive feature was a row of tall neural spines along the vertebrae, creating a ridge or low sail along the back, possibly supporting a fat storage hump or serving as a display structure. Even more significant for the future of predatory dinosaurs was the appearance of early tyrannosaurs. These Cretaceous forms were not yet the massive apex predators they would become. Proceratosaurus from the Middle Jurassic and Guanlong from the Late Jurassic of China represented early members of the tyrannosauroid lineage, but they were small, only 3 to 4 meters long, and occupied mid-tier predatory roles. Throughout the early Cretaceous, tyrannosaurs remained relatively small and uncommon, overshadowed by larger Carcharodontosaurids and other predatory groups. But they were evolving, developing the anatomical features that would eventually make them the most powerful terrestrial predators in Earth's history. Sauropods, which had dominated the Jurassic in such spectacular fashion, continued into the Cretaceous but with significant changes in composition and distribution. The diplodocids and brachiosaurids that had characterized late Jurassic faunas like the Morrison Formation became less common in the early Cretaceous, replaced by new sauropod groups better adapted to the changing world. Titanosaurs emerged as the dominant sauropod lineage during the Cretaceous, eventually achieving global distribution across every continent including Antarctica. Unlike their Jurassic predecessors, many titanosaurs possessed osteoderms, bony armor embedded in the skin, providing protection against the increasingly sophisticated predators of the Cretaceous world. The geographic isolation created by continental breakup had profound effects on dinosaur evolution. In North America during the late Cretaceous, approximately 100 to 66 million years ago, the western interior seaway divided the continent into two landmasses, Laramidia to the west and Appalachia to the east. This shallow sea, stretching from the Gulf of Mexico to the Arctic Ocean, created a north-south barrier that persisted for millions of years. Laramidia, despite being only one-third the size of modern North America, supported extraordinarily diverse dinosaur faunas including tyrannosaurs, ceratopsians, hadrosaurs, and ankylosaurs. Appalachia, the eastern landmass, remains poorly known paleontologically due to limited fossil-bearing rock exposures, but what evidence exists suggests a distinct fauna adapted to the heavily forested, humid conditions of the eastern coastal plain. In Asia, dinosaur faunas took different evolutionary paths. Maniraptoran coelurosaurs, the group including dromaeosaurs, trudontids, and oviraptorosaurs, became the dominant small to medium-sized theropods. These were highly specialized dinosaurs, many possessing feathers, and large brains relative to body size, and complex behaviors including brooding of eggs. Oviraptorosaurs developed toothless beaks, and some species evolved elaborate head crests, suggesting complex visual communication and social behaviors. Therizinosaurs, bizarre pot-bellied theropods with enormously long claws on their hands, evolved into herbivores or omnivores, representing a radical departure from the carnivorous lifestyle of their ancestors. South America and Africa, which remained connected until approximately 100 million years ago, shared similar dinosaur faunas during the early Cretaceous but began diverging as the South Atlantic Ocean widened. Abelisaurids, short-faced, often horned theropods, became the dominant large predators in Gondwana, filling the ecological role that tyrannosaurs occupied in the north. Carcharodontosaurids also thrive in Africa, producing some of the largest terrestrial predators ever to exist, including Giganotosaurus from South America and Carcharodontosaurus from North Africa, both exceeding 12 meters in length and rivaling or exceeding Tyrannosaurus rex in size. The early Cretaceous was a time of experimentation and diversification, as dinosaurs adapted to fragmenting continents, evolving climates, and changing vegetation. New body plans appeared, old lineages were replaced by new ones, and regional faunas became increasingly distinct. The stage was being set for the late Cretaceous, when dinosaur diversity would reach its absolute peak in the final 30 million years before the asteroid impact that would end their reign. The question of when dinosaur diversity peaked has generated considerable scientific debate, but quantitative analyses of the fossil record provide clear answers. The observed diversity of dinosaurs reached its highest levels during the mid to late Cretaceous, particularly the last 50 million years before their extinction. However, distinguishing genuine biological patterns from sampling artifacts, biases introduced by uneven preservation and discovery of fossils, requires sophisticated statistical methods. When paleontologists apply sampling standardization techniques to account for variations in rock availability and collection effort, the picture becomes clearer. Dinosaur diversity increased generally throughout the Mesozoic era, with ornithischians and theropods reaching their absolute peak during the Campanian stage of the late Cretaceous, approximately 83 to 72 million years ago. Sauropodomorphs followed a different trajectory. Their diversity peaked during the late Jurassic, then declined significantly across the Jurassic-Cretaceous boundary, with a loss of 58 to 82% of taxonomic diversity depending on the metric used. Throughout the early and middle Cretaceous, sauropod diversity remained relatively low compared to Jurassic levels, though titanosaurs underwent a modest radiation during the late Cretaceous. Unlike ornithischians and theropods, whose diversity curves show steady increases punctuated by sharp peaks in the Campanian, sauropodomorph diversity remained relatively constant during the final 30 million years of the Cretaceous, neither increasing dramatically nor declining before the final extinction. The Campanian stage, from 83.6 to 72 million years ago, represents the zenith of dinosaur diversity. Fossil formations from this time, particularly the Dinosaur Park Formation in Alberta and the Judith River Formation in Montana, preserve extraordinarily diverse assemblages with more distinct dinosaur genera than any other single group of rocks. These formations contain multiple species of ceratopsians, hadrosaurs, ankylosaurs, pachycephalosaurs, and tyrannosaurs all living contemporaneously in the same ecosystems. This exceptional diversity reflects both genuine biological richness and optimal preservation conditions. The Western Interior Seaway created extensive lowland environments where dinosaurs thrived, and rapid burial in river and coastal sediments preserved their remains with exceptional fidelity. The succeeding Maastrichtian stage, the final interval of the Cretaceous from 72 to 66 million years ago, shows an apparent decline in dinosaur diversity in some regions, particularly North America. Known diversity drops from the Campanian to the Maastrichtian, with approximately 45% fewer genera recorded. However, statistical analyses suggest this decline may be an artifact of sampling bias rather than genuine extinction. The Maastrichtian fossil record is estimated to be only 39% complete at the generic level compared to 48% for the Campanian, meaning that reduced discovery rates rather than reduced actual diversity may explain the apparent decline. When diversity estimation methods that correct for incomplete sampling are applied, Campanian and Maastrichtian diversity appear roughly equivalent, suggesting dinosaurs maintained high diversity right up to the moment of the asteroid impact. Geographic patterns add additional complexity. Latitudinal diversity gradients, the pattern where biodiversity peaks at tropical latitudes and decreases toward the poles, characterize modern ecosystems, but dinosaurs did not follow this pattern. Throughout their 160 million year history, dinosaur diversity was highest at temperate paleolatitudes rather than in tropical zones. This unusual pattern likely resulted from the distribution of land area, with more continental area located at temperate latitudes during the Mesozoic, providing more habitat and ecological opportunity for dinosaur diversification. The Cretaceous period, particularly its latter half, was the age of maximum dinosaur diversity, a time when these animals had filled every available terrestrial niche across every continent, adapting to environments from polar forests to tropical coastlines and ranging in size from chicken-sized insectivores to 80-ton herbivores. This was their evolutionary apex, the culmination of 165 million years of adaptation and diversification. The fragmentation of Pangaea accelerated throughout the early and middle Cretaceous, fundamentally altering the distribution and evolution of terrestrial life. By 120 million years ago, South America and Africa were separating along what would become the South Atlantic Ocean, though narrow land bridges or island chains may have persisted for millions of years, allowing occasional faunal exchange. India, which had been part of Gondwana, began its dramatic northward journey that would eventually carry it across the Tethys Ocean to collide with Asia, creating the Himalayan mountain range, though that collision lay tens of millions of years in the future. Australia and Antarctica remained connected but were drifting southward, carrying their dinosaur populations into increasingly high latitudes where seasonal darkness and cold temperatures, though not freezing, created environmental conditions unlike those anywhere else on Earth. These geographic changes created what paleobiogeographers call vicariance, the splitting of ancestral populations by geographic barriers, leading to independent evolution in isolated regions. The dinosaur faunas of different continents, which had been relatively similar during the Jurassic when Pangaea was still partially connected, began diverging into distinct provincial assemblages. North American dinosaurs of the late Cretaceous would share more similarities with Asian dinosaurs than with their South American counterparts, despite North America and Asia being separated by ocean. This pattern resulted from periodic land connections across the Bering region, creating a dispersal corridor called Beringia that allowed faunal exchange between the northern continents while the southern continents remained isolated. The ornithopods, bipedal and facultatively quadrupedal herbivorous ornithischians, underwent significant diversification during the early and middle Cretaceous, setting the stage for the explosive radiation of hadrosaurs that would dominate late Cretaceous ecosystems. Early ornithopods like Iguanodon, from the early Cretaceous of Europe dating to approximately 126 to 122 million years ago, were large, robust animals reaching lengths of 10 meters and masses of 3 to 4 tons. The skull was equipped with a horny beak at the front for cropping vegetation and batteries of grinding teeth farther back for processing tough plant material. The hands were specialized, with the thumb modified into a conical spike, likely used for defense against predators or in intraspecific combat, while the other fingers retained flexibility for manipulating vegetation. Iguanodon was one of the first dinosaurs ever scientifically described, with fossils discovered in England in the 1820s contributing to the early development of paleontology as a scientific discipline. From ornithopod ancestors like Iguanodon, the hadrosaurs or duck-billed dinosaurs would eventually evolve, developing increasingly sophisticated dental batteries, tightly packed rows of hundreds of teeth that formed continuous grinding surfaces capable of processing the toughest vegetation. But in the early Cretaceous, hadrosaurs had not yet appeared. The iguanodontians represented the pinnacle of ornithopod evolution, and they thrived across multiple continents. Pachycephalosaurs, the thick-skulled dome-headed dinosaurs, also emerged during the early Cretaceous, though they would remain relatively uncommon and restricted primarily to Asia and North America throughout their evolutionary history. These bipedal herbivores possessed massively thickened skull roofs, with bone-forming domes up to 25 centimeters thick in some species. The function of these domes has generated debate, direct headbutting combat, as seen in modern rams and bighorn sheep, was the traditional interpretation, but biomechanical analyses suggest the domes may not have been strong enough to withstand repeated high-impact collisions. Alternative hypotheses include flank butting, where rivals struck each other's sides rather than heads, or purely visual display, where dome size indicated individual fitness without actual combat. The early Cretaceous world was a planet in transition, continents drifting apart, seaways flooding and receding, climates shifting, and dinosaurs adapting to an increasingly fragmented world. The stage was being set for the most transformative botanical revolution in terrestrial history, the emergence and explosive radiation of flowering plants, which would fundamentally restructure ecosystems and drive the final phase of dinosaur evolution toward its spectacular late Cretaceous climax. For over 200 million years, from the Devonian period through the first half of the Cretaceous, terrestrial plant life had been dominated by gymnosperms, seed plants including conifers, cycads, ginkgos, and seed ferns, along with ferns and other spore-producing plants. These plants had sustained ecosystems through multiple mass extinctions, supported the evolution of dinosaurs from their origins through their Jurassic zenith, and created forests that stretch across every continent. But approximately 130 million years ago, during the early Cretaceous, something unprecedented appeared in the fossil record. Angiosperms, the flowering plants, emerged with a suite of innovations that would fundamentally restructure terrestrial ecosystems and drive the final phase of dinosaur evolution. The earliest definitive fossil evidence of flowering plants comes from the Valanginian stage of the early Cretaceous, approximately 140 to 133 million years ago, preserved as pollen grains in sedimentary rocks from multiple continents. These microscopic fossils represent the first unambiguous traces of angiosperm existence. By the Albian stage, approximately 113 to 100 million years ago, the middle of the Cretaceous, flowering plant fossils became dramatically more abundant, indicating rapid diversification and geographic expansion. Fossil flowers from southern China and South America dating to this period show simple structures, small blossoms with basic petal arrangements, lacking the elaborate specializations that would evolve later through coevolution with insect pollinators. What made angiosperms revolutionary was not any single feature, but rather a combination of innovations that conferred enormous competitive advantages. The defining characteristic was the enclosed ovule, seeds protected within a carpel, the female reproductive structure that would develop into a fruit after fertilization. Gymnosperms, by contrast, bore exposed seeds on cones or modified leaves, leaving them vulnerable to desiccation, predation, and environmental damage. The enclosed seed of angiosperms provided protection and allowed for the development of fruit, fleshy structures that attracted animals to eat the seeds and disperse them across vast distances in their digestive systems. This animal-mediated dispersal was far more efficient than the wind dispersal relied upon by most gymnosperms, allowing angiosperms to colonize new habitats rapidly. Flowers themselves represented a targeted, reproductive strategy. Rather than producing enormous quantities of pollen and relying on wind to carry it to receptive female structures, an inefficient process with high resource costs, angiosperms developed flowers that attracted specific pollinators, particularly insects. Bright colors, distinctive scents, nectar rewards, and specialized structures evolved to attract bees, flies, beetles, and other insects that would transfer pollen directly from one flower to another with far greater efficiency than wind pollination. The rise of insect pollinators around 100 million years ago created a coevolutionary relationship. As flowers evolved more specialized features to attract pollinators, insects evolved specialized adaptations, long tongues, specific body shapes, sensory capabilities to exploit floral resources. This reciprocal evolution accelerated the diversification of both groups. Perhaps most importantly, angiosperms possessed remarkable growth rates and reproductive flexibility. Many early angiosperms were fast-growing herbaceous plants, non-woody vegetation that could complete its life cycle rapidly, produce seeds quickly, and colonize disturbed environments before slower-growing gymnosperms could establish themselves. This pioneering ability allowed angiosperms to exploit ecological opportunities with unprecedented speed. Additionally, Many angiosperms developed efficient photosynthetic pathways and leaf structures with high surface area-to-volume ratios, maximizing carbon capture and growth rates. In the warm, CO2-rich atmosphere of the mid-Cretaceous, with carbon dioxide levels estimated at 1,000 to 1,500 parts per million, these efficient photosynthetic systems gave angiosperms substantial competitive advantages. The spread of flowering plants across the Cretaceous landscape was explosive by geological standards. By the Maastrichtian stage, the final interval of the Cretaceous from 72 to 66 million years ago, angiosperms represented approximately 70 of terrestrial plant species. Gymnosperms, which had dominated for over 150 million years, found their ranges contracting as flowering plants invaded habitats from coastal lowlands to mountain slopes. By the end of the Cretaceous, large canopy-forming angiosperm trees, early relatives of modern magnolias, dogwoods, and oaks, had replaced conifers as the dominant forest trees in many regions, fundamentally altering the structure, productivity, and resource availability of terrestrial ecosystems. For herbivorous dinosaurs, this botanical revolution created both challenges and opportunities. Gymnosperms and ferns, the traditional food sources, had relatively tough tissues with high proportions of cellulose and lignin, structural compounds difficult to digest. Angiosperms, particularly herbaceous species and deciduous trees, often produce softer, more nutritious foliage with higher protein content and lower fiber content. However, many angiosperms also evolved chemical defenses, toxic compounds, bitter-tasting alkaloids, and digestive inhibitors to deter herbivores from consuming them. The dinosaurs that could adapt their feeding strategies, jaw mechanics, and digestive systems to exploit these new food sources while managing their chemical defenses would gain access to resources that were more abundant and nutritious than anything available in the gymnosperm-dominated world of the Jurassic. The evolutionary response of herbivorous dinosaurs to the angiosperm revolution was profound and measurable. Hadrosaurs, the duck-billed dinosaurs, emerged during the Middle Cretaceous, and by the Late Cretaceous had become the most abundant large herbivores in North America and Asia. Their success was directly linked to dental innovations that allowed them to process the tough, chemically defended tissues of flowering plants. Hadrosaur jaws contained dental batteries consisting of hundreds of tightly packed teeth arranged in multiple rows, with as many as 6 replacement teeth beneath each functional tooth. As teeth wore down from grinding vegetation, new teeth continuously moved into position, creating self-sharpening grinding surfaces capable of pulverizing even the toughest plant material. The sophistication of hadrosaur dental batteries exceeded anything seen in earlier ornithopods. In primitive ornithopods like Iguanodon, teeth were arranged in single functional rows with limited occlusion. The upper and lower teeth did not meet precisely during chewing. Hadrosaurs, by contrast, developed precise tooth-to-tooth occlusion, with upper and lower dental batteries forming continuous grinding surfaces that moved past each other like millstones. This allowed them to thoroughly process plant material before swallowing, extracting maximum nutritional value for vegetation that would have been indigestible to earlier dinosaurs. Microscopic analysis of wear patterns on hadrosaur teeth reveals striations and polishing consistent with processing both tough gymnosperms and softer angiosperms, suggesting dietary flexibility that allowed them to exploit whatever vegetation was most abundant seasonally. Ceratopsians, the horned dinosaurs, followed a different evolutionary path but achieved similar success. Early ceratopsians like Psittacosaurus from the early Cretaceous were small and lightly built, but by the late Cretaceous, the group had produced some of the largest and most heavily armored herbivores in North America. Triceratops, the iconic three-horned giant that would appear in the final few million years before the asteroid impact, weighed up to 12 tons and possessed a massive skull with a powerful beak and batteries of shearing teeth designed for slicing through tough vegetation. The elaborate frills and horns that characterize late Cretaceous ceratopsians likely served multiple functions: defense against predators, thermoregulation, and intraspecific display, and combat for territory or mates. The expansion of flowering plants also affected sauropods, though less dramatically. Titanosaurs, the dominant Cretaceous sauropod group, showed morphological changes compared to their Jurassic predecessors. Many titanosaur species were smaller than the giant diplodocids and brachiosaurids of the Morrison Formation, with body masses in the 10 to 20 ton range rather than 30 to 80 tons. This size reduction may reflect changes in vegetation structure. Angiosperm-dominated forests had different vertical profiles than conifer forests, potentially providing less high canopy brows that had supported the enormous neck lengths of Jurassic sauropods. Additionally, many titanosaurs developed osteoderms, bony armor plates embedded in the skin, suggesting increased predation pressure from the sophisticated theropods of the late Cretaceous. The flowering plant revolution thus drove a cascade of evolutionary changes throughout Cretaceous ecosystems. Herbivorous dinosaurs that could efficiently process angiosperm vegetation, hadrosaurs with their grinding dental batteries, ceratopsians with their powerful shearing beaks, flourished and diversified. Predators evolved in response, developing increasingly sophisticated hunting adaptations to pursue these new prey species. By the late Cretaceous, ecosystems in North America and Asia were fundamentally different from those of the Jurassic, structured around flowering plants and the specialized herbivores that consumed them. This was the botanical revolution that reshaped the Mesozoic world and set the stage for the final, most diverse phase of dinosaur evolution. The transformation of terrestrial ecosystems by flowering plants extended beyond herbivore adaptations to reshape entire food webs. As angiosperms spread across the mid to late Cretaceous landscape, they fundamentally altered primary productivity patterns, the rate at which plant biomass was generated, and this had cascading effects throughout ecosystems. Flowering plants, with their efficient photosynthesis and rapid growth cycles, could produce more biomass per unit area than the gymnosperm-dominated forests of the Jurassic. This increased productivity supported larger populations of herbivorous dinosaurs, which in turn supported more diverse and abundant predator communities. The structural changes in vegetation were equally significant. Angiosperm forests had different vertical stratification than conifer forests. Deciduous broadleaf trees created more complex canopy structures with distinct layers, emergent trees reaching the highest levels, a continuous canopy layer below, an understory of smaller trees and shrubs, and a ground layer of herbaceous plants and leaf litter. This architectural complexity created more ecological niches, specific roles and habitats, than the relatively uniform vertical structure of conifer forests. Small dinosaurs, early mammals, and other vertebrates could exploit these different vertical zones, leading to increased overall biodiversity in angiosperm-dominated ecosystems. The seasonal dynamics of angiosperm ecosystems also differed from gymnosperm forests. Many flowering plants were deciduous, shedding their leaves seasonally in response to temperature or precipitation changes. This created seasonal pulses of leaf litter, concentrated periods when enormous quantities of dead plant material fell to the ground, providing resources for decomposers and detritivores in cycling nutrients back into the soil. Gymnosperm forests, dominated by evergreen conifers and cycads, had more continuous but less dramatic leaf fall. The seasonal resource pulses in angiosperm ecosystems would have created temporal variation in food availability, potentially driving seasonal migration patterns in herbivorous dinosaurs as they follow the availability of fresh vegetation. By the Campanian and Maastrichtian stages of the late Cretaceous, approximately 83 to 66 million years ago, angiosperm-dominated ecosystems had reached their full development. Fossil plant assemblages from this time include recognizable ancestors of modern plant families, early oaks, magnolias, palms, and many others. The Hell Creek Formation of Montana and the Dakotas, which preserves the final few million years of the Cretaceous, contains diverse angiosperm floras alongside the famous dinosaur fauna that included Tyrannosaurus rex, Triceratops, and Edmontosaurus. These dinosaurs evolved in and were adapted to angiosperm-dominated landscapes. They were fundamentally products of the flowering plant revolution. The rise of flowering plants represents one of the most consequential evolutionary events in terrestrial history. It restructured ecosystems from the ground up, drove the final diversification of herbivorous dinosaurs, and created the ecological template that would persist after the asteroid impact when mammals inherited the Earth. The dinosaurs of the late Cretaceous were not Jurassic holdovers persisting in unchanging environments, They were highly evolved, specialized creatures adapted to complex, productive ecosystems built on flowering plants. This was their world, and for 30 million years, they thrived in it. The traditional image of dinosaurs as scaly, reptilian monsters underwent a revolutionary transformation beginning in the 1990s with a series of extraordinary fossil discoveries from northeastern China. The Yixin Formation and related deposits in Liaoning Province, dating to approximately 125 to 120 million years ago during the early Cretaceous began, yielding fossils of unprecedented preservation quality, dinosaurs with soft tissue details preserved, including the unmistakable impressions of feathers. These discoveries demolished the artificial barrier that had been erected between dinosaurs and birds, revealing instead a continuous evolutionary gradient from fully terrestrial theropods to powered flyers, with feathers appearing long before flight itself evolved. The first feathered non-avian dinosaur to capture worldwide scientific attention was Sinosauropteryx prima, described in 1996 from a nearly complete skeleton approximately 1 meter in length. The fossil showed a halo of filamentous structures surrounding the body and extending along the tail, simple, hollow fibers that represented the most primitive form of feathers, called protofeathers. These structures were not the complex, vain feathers of modern birds capable of supporting flight. Instead, they were simple integumentary outgrowths, more similar to hair than flight feathers, serving functions related to insulation rather than aerodynamics. The presence of these structures on a small theropod that was clearly incapable of flight demonstrated conclusively that feathers did not evolve for flight. They evolved first for thermoregulation, and flight came later as a secondary adaptation. Subsequent discoveries expanded the diversity of feathered dinosaurs dramatically. Caudipteryx, also from the Yixin Formation, was a turkey-sized oviraptorosaur with clearly preserved symmetrical feathers on its arms and tail, feathers with central shafts and barbs creating flat surfaces, though the symmetrical shape indicated they were not flight feathers. Protarchaeopteryx showed similar features. These animals were running, ground-dwelling dinosaurs that happened to be covered in feathers, using them for display, species recognition, courtship, or temperature regulation in the seasonal climate of early Cretaceous China. Microraptor guay, described in 2003, represented something even more extraordinary. A small dromaeosaurid approximately 80 centimeters long with asymmetrical flight feathers on both its arms and legs, creating a four-winged configuration unique among known dinosaurs. The asymmetry of the feathers, with the leading edge narrower than the trailing edge, is the diagnostic feature of flight feathers in modern birds, creating the airfoil shape necessary for generating lift. Analysis of Microraptor specimens, some of which preserve even the microscopic structures that would have determined feather coloration, suggests these animals were capable of gliding and possibly powered flight, though their four-winged configuration represented an evolutionary experiment that would not persist. Modern birds are strictly two-winged. The fossils from Liaoning Province preserved not just feathers but their microscopic structure. Melanosomes, organelles that contain pigments, were identified in fossilized feathers, and their size, shape, and arrangement could be compared to those in modern bird feathers to reconstruct coloration. Sinosauropteryx appears to have had reddish-brown and white banding along its tail. Anchiornis, a small Paravian dinosaur closely related to birds, showed black and gray body plumage with white limbs and distinctive reddish-brown head plumage. Microraptor had iridescent black plumage similar to modern crows. These were not drab, colorless creatures. They were as vibrant and visually striking as modern birds, using their plumage for display and communication. The distribution of feathers across theropod phylogeny reveal that feathers were not limited to bird ancestors, but appeared across multiple lineages. Tyrannosauroids, the group that would eventually produce Tyrannosaurus rex, showed evidence of feathering in their smaller, earlier members. Delong paradoxus, a tyrannosauroid from the Yixin Formation approximately 1.6 meters long, preserved simple filamentous feathers. Uteranus huali, a much larger tyrannosauroid from slightly younger deposits reaching 9 meters in length and weighing approximately 1,400 kilograms, also showed extensive feather coverage, demonstrating that even large theropods retained feathers, at least in the cool climates of early Cretaceous Asia. Whether the giant late Cretaceous tyrannosaurs like T-Rex retained feathers or lost them due to the thermoregulatory challenges of maintaining such massive bodies in warmer climates remains debated, with evidence from skin impressions suggesting that at least parts of their bodies were covered in scales. The evolutionary pathway from ground-dwelling feathered dinosaurs to powered flyers involved multiple intermediate stages, and the fossil record preserved many of them. The earliest known bird, Archaeopteryx lithographica from the late Jurassic Solnhofen limestone of Germany, dating to approximately 150 million years ago, showed a mosaic of dinosaurian and avian features, teeth, clawed fingers, and a long bony tail like a theropod dinosaur, but with fully developed asymmetrical flight feathers and a wishbone formed from fused clavicles. Specimens of Archaeopteryx preserved with wings spread show wing configurations similar to modern birds, and biomechanical analyses suggest these animals were capable of powered flight, though perhaps not with the sustained, efficient flight of modern birds. The Cretaceous period witnessed an explosion of avian diversity as birds evolved from their theropod ancestors and radiated into numerous ecological niches. By 125 million years ago, multiple bird lineages coexisted in early Cretaceous China, preserved in the exceptional fossil deposits of Liaoning province. These early birds showed progressive refinements of flight adaptations while retaining varying degrees of their dinosaurian heritage. Confucius ornis, one of the most common early Cretaceous birds with over 1,000 specimens recovered, possessed a toothless beak unlike Archaeopteryx, representing a significant step toward modern bird anatomy. Males had elaborate tail feathers extending far beyond the body, clear evidence that sexual selection through display was driving feather evolution in addition to aerodynamic considerations. The evolutionary stages of feather development can be traced through the theropod fossil record with remarkable clarity. The phylogenetically earliest feathers documented in theropods were simple monofilaments, single hollow tubes made primarily of keratin, similar in structure to hair. Cinerumimus, a megalosauroid from the late Jurassic of Germany, preserved these simple filamentous structures. The second evolutionary stage involved branching, where individual filaments split either radially or bilaterally, creating structures resembling down feathers. Delong and Sinosauropteryx preserved these branch filaments. The third stage saw the development of pinnaceous feathers with symmetrical veins, feathers with a central shaft and lateral branches forming flat surfaces on either side. These appeared in early Penaraptorans and served functions including insulation, waterproofing, and display. The fourth and final stage was the evolution of asymmetrical veins, feathers where the central shaft runs closer to the leading edge than the trailing edge, creating the aerodynamic profile necessary for powered flight. These flight feathers appeared in paravians, the group including birds and their closest dinosaurian relatives. This evolutionary sequence is remarkable because it is recapitulated in the development of modern bird feathers, a stunning example of ontogeny recapitulating phylogeny. When a feather grows in a modern bird, it begins as a simple tubular structure, then develops branches, then a central shaft forms as the branches fuse at their bases, and finally the sheath disintegrates and a mature feather unfurls. This developmental sequence mirrors the evolutionary history preserved in the fossil record, providing independent confirmation of the evolutionary pathway. Not all feathered theropods were small. Uteranus huali, a tyrannosauroid from early Cretaceous China, reached 9 meters in length and weighed approximately 1,400 kilograms, making it the largest known feathered animal. The extensive feather coverage on such a large animal indicates that feathers serve important thermoregulatory functions even in animals too large to face significant heat loss problems. The climate of early Cretaceous Liaoning was seasonal and relatively cool, with average annual temperatures estimated at 10 degrees Celsius, conditions where insulating feathers would have provided significant advantages for maintaining stable body temperatures and remaining active during cold periods. The question of whether large late Cretaceous theropods like Tyrannosaurus rex retained feathers remains unresolved. Skin impressions from several large tyrannosaurids show scales rather than feathers on parts of the body, suggesting that as tyrannosaurs increased in size and moved into warmer climates during the late Cretaceous, they may have reduced or lost their feather covering to avoid overheating. Large animals have lower surface area-to-volume ratios than small animals, making heat dissipation more challenging than heat retention. Modern large mammals like elephants and rhinoceroses have reduced hair coverage for this reason. However, it remains possible that even large tyrannosaurs retain feathers on some body regions, the back for example, where sun exposure would be greatest, while having scales on other regions. The fossil record demonstrates unequivocally that feathers evolved in non-flying dinosaurs tens of millions of years before birds achieved powered flight. Feathers served multiple functions throughout their evolutionary history: insulation in cool climates, waterproofing, camouflage, species recognition, sexual display, and egg brooding before they were co-opted for aerodynamic purposes. The discovery of feathered dinosaurs revolutionized paleontology, transforming dinosaurs from extinct reptilian monsters into the direct ancestors of the 10,000 species of birds alive today, living dinosaurs that never went extinct. The evolutionary transition from Archaeopteryx to modern birds continued throughout the Cretaceous period, with each successive stage refining the avian body plan. The Cretaceous saw emergence of increasingly bird-like forms that progressively lost their dinosaurian characteristics while perfecting adaptations for flight. Ichthyornis dispar, a seagull-sized bird from the late Cretaceous of North America dating to approximately 86 million years ago, represented a critical intermediate stage. This animal possessed a modern bird brain and a beak at the front of its jaws, but the beak was lined with sharp teeth, and the jaw structure retained the powerful mechanics of predatory dinosaurs like Velociraptor. The skull was a mosaic of features, part bird, part dinosaur, demonstrating that the evolution from dinosaurs to birds was gradual rather than instantaneous. The anatomical changes that occurred during the dinosaur-bird transition were extensive and involved virtually every body system. The skeleton underwent progressive reduction and fusion of bones, increasing structural efficiency for flight. The long bony tail of theropod dinosaurs was reduced to a pygostyle, a short stump formed from fused vertebrae, which provided attachment for a spray of tail feathers that improved aerial stability and maneuverability. The hand bones fused and consolidated, with the wrist taking on a semicircular form that allowed the wing to rotate sideways against the forearm, creating the joint motion necessary for generating thrust during flight. The fourth and fifth digits were completely lost, streamlining the wing structure. The wishbone, present in non-avian theropods, became stronger and more elaborate in birds, and the shoulder girdle evolved to connect with an enlarged breastbone that developed a prominent keel along its midline, the anchor point for powerful flight muscles. Feathers themselves underwent refinement. The asymmetrical flight feathers became longer and more aerodynamically sophisticated, with precise vane shapes optimized for generating lift and minimizing drag. The bone walls became progressively thinner. Hollow bones that were already present in theropod dinosaurs became even more pneumatized in birds, reducing weight to the absolute minimum while maintaining strength through internal strutting. The respiratory system, already efficient in theropod dinosaurs with flow-through lungs and air sacs, became perfected in birds, delivering the high oxygen throughput necessary for sustained powered flight, one of the most energetically demanding forms of locomotion in nature. Growth rates and metabolic systems also evolved. Birds inherited rapid growth and elevated metabolic rates from their theropod ancestors, but these traits became even more pronounced. The microscopic structure of bird bone shows growth patterns intermediate between cold-blooded reptiles and fully warm-blooded mammals, indicating that birds, and likely their theropod ancestors, possessed metabolic rates and thermoregulatory capabilities that enabled them to remain active regardless of environmental temperatures. By the end of the Cretaceous, multiple lineages of birds had evolved, though most would not survive the asteroid impact. Modern birds, neornids, originated in the late Cretaceous, and were the only bird lineage to survive the mass extinction 66 million years ago that eliminated all non-avian dinosaurs. From this surviving lineage, the 10,000 bird species alive today radiated during the Paleogene, eventually becoming the most diverse group of land vertebrates. The fossil record of the dinosaur-bird transition stands as one of the most complete evolutionary sequences documented in paleontology. From simple filamentous protofeathers in early Jurassic theropods, through the four-winged gliders of the early Cretaceous, to the toothed beaked birds of the late Cretaceous, to the modern birds of today, each stage is preserved in stone. Birds are not descended from dinosaurs. They are dinosaurs, the only lineage to survive the Cretaceous extinction and continue evolving into the present day, the world of 66 million years ago. In the final moments of the Maastrichtian stage of the late Cretaceous represented the culmination of 165 million years of dinosaur evolution. Dinosaurs had achieved global distribution, occupying every terrestrial environment from polar forests to tropical coastlands. They ranged from chicken-sized insectivores to 80-ton herbivores, from swift bipedal predators to heavily armored quadrupeds. In North America, the Hell Creek Formation preserves a snapshot of this final dinosaur world. Tyrannosaurus rex ruled as apex predator, hunting herds of Triceratops and Edmontosaurus across floodplains vegetated with flowering plants. In Asia, different but equally diverse faunas thrived. In South America, abelosaurid theropods and titanosaur sauropods dominated. On every continent except Antarctica, which was forested but isolated at the South Pole, dinosaurs were the preeminent terrestrial vertebrates. There is no evidence that dinosaurs were in decline. Earlier hypotheses suggesting gradual extinction before the asteroid impact have been refuted by careful statistical analysis, accounting for sampling biases in the fossil record. Dinosaur diversity in the final 10 million years of the Cretaceous remained high, with no detectable downward trend. The Hell Creek Formation, which spans the last 2 million years of the Cretaceous and the first million years of the Paleogene, shows abundant and diverse dinosaur fossils right up to the boundary layer, the thin stratum marking the moment of impact. Above that layer, there are no non-avian dinosaur fossils. The extinction was geologically instantaneous. The asteroid that ended the age of dinosaurs originated in the asteroid belt between Mars and Jupiter. Chemical analysis of the thin clay layer deposited globally at the Cretaceous-Paleogene boundary, a layer that marks the exact moment in geological time 66 million years ago, reveals that the impactor was a carbonaceous chondrite, a type of stony asteroid rich in water and organic compounds dating to the early solar system. The asteroid measured between 10 and 15 kilometers in diameter, roughly the size of Mount Everest. It approached Earth from the northeast at approximately 20 kilometers per second, striking at an angle of roughly 60 degrees above horizontal, the optimal angle for maximizing atmospheric ejection of vaporized rock. The impact site was the shallow waters off what is now the Yucatan Peninsula in Mexico. The asteroid struck sedimentary rocks rich in gypsum, hydrated calcium sulfate, along with carbonates and other evaporite minerals. The kinetic energy of impact was staggering, the equivalent of approximately 10 billion Hiroshima atomic bombs, or 100 million megatons of TNT. This energy converted instantaneously to heat. The asteroid did not simply explode. It vaporized, along with the target rocks. The impact created a crater 150 to 180 kilometers in diameter and excavated rocks from deep within Earth's crust, lifting them 25 kilometers into the air. A rim of mountains taller than the Himalayas formed instantaneously around the crater's edge. The Chicxulub crater, as it is now called, is one of the largest impact structures on Earth. The immediate devastation extended for thousands of kilometers. Seismic waves equivalent to magnitude 10 or 11 earthquakes radiated outward, magnitudes far exceeding anything in recorded human history. The impact triggered massive tsunamis that swept across the Gulf of Mexico and the Atlantic Ocean, with wave heights exceeding 100 meters. Coastal regions throughout the Americas were inundated. The heat pulse from vaporized rock ignited wildfires across North America and possibly globally. Geological evidence from the Tanis site in North Dakota, part of the Hell Creek Formation, located approximately 3,000 kilometers from the impact site, preserves what appears to be a snapshot of the day of impact. Fish fossils with impact spherules lodged in their gills, jumbled deposits suggesting seiche waves, standing waves in enclosed water bodies caused by seismic shaking, and amber containing microtectites. Tiny glass beads formed from rock vaporized by the impact and flash-cooled in the atmosphere. But the immediate devastation, catastrophic as it was, affected only a fraction of the planet. The global extinction resulted from longer-term environmental changes triggered by the impact. The vaporization of sulfur-rich gypsum released an estimated 325 billion tons of sulfur into the atmosphere in the form of sulfur dioxide. This combined with water vapor to form sulfuric acid aerosols, tiny droplets suspended in the stratosphere that reflected sunlight back into space. Additionally, the impact ejected approximately 15 trillion tons of fine silicate dust into the upper atmosphere. This combination of sulfuric acid aerosols and dust created a global shroud that blocked sunlight from reaching Earth's surface. The duration of darkness has been calculated through multiple independent methods. Climate models incorporating the volume of ejected dust and sulfuric acid aerosols estimate that photosynthesis would have been severely reduced or completely halted for approximately 18 to 24 months across much of the planet. Analysis of sediments from the Hell Creek Formation suggests the darkness persisted for nearly 2 years in North America. During this time, global temperatures plummeted. The initial heat pulse from the impact gave way within hours to rapid cooling as sunlight was blocked. Surface temperatures may have dropped by 20 to 28 degrees Celsius, creating freezing conditions even in tropical regions that had not experienced frost in millions of years. The collapse of photosynthesis triggered cascading ecological disasters. On land, plants died or went dormant. Without photosynthesis producing the glucose that fueled terrestrial ecosystems, herbivores had nothing to eat. Fossil leaf assemblages from immediately after the boundary show a dramatic decline in diversity. Approximately 57 of plant species in North America went extinct. Those that survived were predominantly species with resilient strategies, plants that produce seeds or spores capable of remaining dormant for years, waiting for conditions to improve. The fossil record shows what paleobotanists call a fern spike, a brief interval after the impact when fern spores dominated sediments, indicating that fast-growing, opportunistic ferns colonized the devastated landscape before other plants could recover. Herbivorous dinosaurs, which required enormous quantities of fresh vegetation daily to sustain their metabolism, faced starvation. Large herbivores have lower mass-specific metabolic rates than small animals, meaning they can survive longer without food, but they also require far more total food intake. A multi-ton hadrosaur or ceratopsian needed hundreds of kilograms of vegetation per day. When vegetation died off, herbivore populations collapsed within weeks to months. The predators that depended on herbivores followed. A Tyrannosaurus rex weighing 8 tons needed approximately 300 kilograms of meat per week. As prey populations crashed, predator populations collapsed. Within months to years, all non-avian dinosaurs on land were extinct. The marine realm experienced parallel devastation. Phytoplankton, microscopic photosynthetic organisms forming the base of marine food chains, died when sunlight was blocked. Analysis of marine microfossils from the boundary interval shows that approximately 93 of calcareous nanoplankton species went extinct. Larger zooplankton that fed on phytoplankton starved. Fish that fed on zooplankton followed. Marine reptiles like mosasaurs and plesiosaurs, which occupied top predator positions, had no prey base and went extinct. Approximately 75 of all species on Earth vanished within a geologically brief interval, estimated at less than 10,000 years. Yet survival was not random. Organisms with certain characteristics survived preferentially. Small body size conferred advantages. Smaller animals required less food and could survive on scavenged resources. Animals capable of eating seeds, detritus, or carrion survived better than specialized feeders. Freshwater ecosystems experienced lower extinction rates than marine or terrestrial systems, possibly because they were buffered by detritus-based food chains that did not immediately depend on photosynthesis. Crocodilians, turtles, and champsosaurs, semi-aquatic reptiles, survived. Small mammals, which have remained small and nocturnal throughout the Mesozoic, survived. Birds survived, though most Cretaceous bird lineages went extinct, with only the lineage leading to modern birds persisting. The world that emerged from the darkness 2 years after impact was profoundly changed. The age of dinosaurs, which had lasted 165 million years, was over. The Cenozoic era, the age of mammals, was beginning. Recovery from the extinction was neither immediate nor uniform. When sunlight finally penetrated the atmosphere after approximately 2 years of darkness, the world that emerged was radically simplified. Plant communities had collapsed to pioneer species, ferns, mosses, and seed-producing plants that had survived as dormant propagules buried in soil or sediment. The lush forests that had covered much of the late Cretaceous landscape were gone, replaced by low-diversity assemblages dominated by opportunistic species adapted for rapid colonization of disturbed habitats. Paleobotanical evidence from sites in North America shows that it took approximately 1.4 million years for plant diversity to return to pre-extinction levels, and the composition of plant communities was fundamentally different from those of the Cretaceous. Animal communities recovered even more slowly. The fossil record from the early Paleocene, the first epoch of the Cenozoic era, beginning 66 million years ago, shows dramatically reduced diversity compared to the late Cretaceous. In North America, the number of mammal species dropped from approximately 100 before the extinction to around 20 immediately afterward. The survivors were predominantly small. The largest Paleocene mammal was approximately the size of a modern raccoon. These animals were generalists, capable of eating diverse foods including seeds, insects, and plant material. The specialized herbivores and carnivores that had characterized late Cretaceous mammal communities were gone. But the elimination of dinosaurs created evolutionary opportunities that mammals had never possessed during the preceding 165 million years. Throughout the Mesozoic, mammals had remained small, nocturnal, and ecologically marginal, constrained by competition and predation from dinosaurs that occupied every major terrestrial niche. With dinosaurs eliminated, ecological roles from large herbivore to apex predator were vacant, and mammals, the most diverse surviving group of medium to large terrestrial vertebrates, began an adaptive radiation that would reshape terrestrial ecosystems. The pace of mammalian evolution accelerated dramatically during the Paleocene. By 10 million years after the extinction, by 56 million years ago, mammals had diversified into numerous distinct lineages and had begun exploring body sizes and ecological roles unavailable to them during the Mesozoic. The first large herbivorous mammals appeared, including early members of groups that would eventually produce horses, rhinoceroses, and elephants. Carnivorous mammals evolved, filling predatory niches. Primates emerged, exploiting arboreal habitats in recovering forests. Marine mammals appeared, with cetaceans, whales, and dolphins, evolving from terrestrial ancestors and returning to aquatic environments. By the Eocene epoch, approximately 56 to 34 million years ago, mammals had achieved diversity and ecological dominance comparable to what dinosaurs had possessed during the Cretaceous. The evolution of sauropods into giants coincided with warm, humid Jurassic climates that supported extensive conifer forests and high primary productivity. The diversification of hadrosaurs, ceratopsians, and other late Cretaceous herbivores tracked the radiation of flowering plants, which restructured ecosystems and created new food resources. Climate was not a static background against which evolution occurred. It was an active force shaping what was possible, determining which body plans succeeded, and setting the boundaries within which natural selection operated. Recent research suggests that dinosaurs may have experienced population declines beginning approximately 76 million years ago, 10 million years before the asteroid impact, due to gradual global cooling. Temperatures dropped by an estimated 7 degrees Celsius, creating conditions less favorable for animals that relied on warm environments. The loss of herbivorous dinosaur diversity destabilized ecosystems, affecting predators and other organisms dependent on those food webs. This pre-existing stress may have made dinosaur populations more vulnerable when the asteroid struck, though debate continues regarding whether this decline was genuine or an artifact of incomplete fossil sampling. The asteroid impact itself demonstrates how rapidly stable ecosystems can collapse when environmental conditions change beyond the tolerance limits of dominant organisms. Dinosaurs had thrived for 165 million years, adapting to ice-free climates, volcanic eruptions, sea level changes, and continental drift. They had survived previous environmental crises and evolved remarkable diversity. Yet when conditions changed too rapidly, When global temperatures plummeted and photosynthesis ceased for nearly 2 years, their adaptations became irrelevant. Size, which had been advantageous for so long, became a liability. Specialization, which had allowed exploitation of specific resources, became a trap when those resources vanished. The extinction was not a failure of evolution. It was the consequence of environmental change so rapid and severe that adaptation was impossible. The selectivity of extinction provides insights into what determines survival during catastrophic events. Small body size, dietary flexibility, ability to enter dormancy or torpor, and occupation of buffered environments like freshwater systems or underground burrows all increase survival probability. These are not characteristics that would necessarily be advantageous during normal times. They are specifically adaptive for surviving environmental catastrophes. The organisms that inherited the post-impact Earth were not those best adapted to late Cretaceous conditions. They were those whose pre-existing characteristics happened to be useful during the brief but devastating interval when normal rules were suspended. The parallels between the dinosaur extinction and current environmental changes are sobering. Research analyzing late Cretaceous food webs reveals that the structure of ecosystems immediately before the asteroid impact made the extinction more severe than it might have been. Computer simulations reconstructing terrestrial food webs from 17 Cretaceous ecological communities show that the youngest communities, those existing within 2 million years of the impact, were more vulnerable to collapse from plant die-offs than communities from earlier periods. Changes in key ecological groups, including herbivorous dinosaurs like Triceratops and small mammals, altered food web structure in ways that reduced resilience when the asteroid struck. This finding carries profound implications. The late Cretaceous ecosystems were not on the verge of collapse. They would have continued successfully indefinitely under normal conditions. But seemingly innocuous changes to ecosystem structure, likely driven by environmental factors including the drying of the western interior seaway that had covered much of North America, created vulnerabilities that became catastrophic when extreme disturbance occurred. The lesson is clear. Ecosystems can appear stable and productive while accumulating hidden fragilities that only reveal themselves during crises. Simply having high species diversity does not ensure resilience. The types of species present and their functional roles within food webs matter as much as raw numbers. Current research suggests that human activities are creating similar vulnerabilities in modern ecosystems. Habitat fragmentation isolates populations, reducing genetic diversity and limiting species' abilities to migrate in response to changing conditions. Selective pressures from hunting and fishing remove large-bodied species, altering predator-prey dynamics and ecosystem structure. Introduction of invasive species disrupts ecological relationships that evolved over millions of years. Climate change forces species to shift their ranges or adapt to new conditions at rates unprecedented in natural history. Each change individually may seem manageable, but collectively they are restructuring ecosystems in ways that could reduce their capacity to withstand unexpected disturbances. The current biodiversity crisis is now recognized by scientists as representing Earth's sixth mass extinction event. Species are disappearing at rates estimated to be 100 to 1,000 times higher than background extinction rates preserved in the fossil record. Wildlife populations have declined by an average of 68 since 1970 due to habitat destruction, overhunting, pollution, climate change, and invasive species. Unlike the asteroid impact that killed the dinosaurs, an unpredictable catastrophe from space, the current extinction is caused by human activities and is therefore potentially preventable. The question facing humanity is whether we can learn from deep time. Dinosaurs could not have predicted or prevented the asteroid impact. We, however, understand the causes of current environmental degradation and possess the technological capability to address them. The challenge is not knowledge but collective action, the willingness to make changes to economic systems, consumption patterns, and land use practices before ecosystem vulnerabilities accumulate to the point where recovery becomes impossible. The fossil record teaches that recovery from mass extinctions takes millions of years. After the Cretaceous extinction, mammal diversity took 1.4 million years to return to pre-extinction levels, and ecosystem structure remained fundamentally altered. The survivors were not those best adapted to pre-extinction conditions, but those possessing characteristics: small size, dietary flexibility, ability to survive on limited resources that proved useful during the crisis. Humanity cannot assume that our species would survive or thrive in a post-collapse world. We are large-bodied, ecologically specialized, and dependent on complex agricultural and technological systems that require stable environmental conditions. The traits that make modern civilization possible are precisely those that would become liabilities during environmental catastrophe. The dinosaur extinction also reveals uncomfortable truths about the relationship between dominance and vulnerability. Dinosaurs were the most successful terrestrial vertebrates in Earth's history by virtually every measure: duration of reign, geographic distribution, morphological diversity, ecological dominance, and range of body sizes. They thrived across 165 million years, weathering numerous environmental changes and adapting to every terrestrial habitat. Yet this success did not protect them when conditions changed beyond their physiological tolerances. The asteroid impact created an environmental catastrophe so severe and rapid that even 165 million years of evolutionary refinement could not save them. This challenges the notion that evolutionary success guarantees persistence. Species do not evolve towards some abstract perfection. They evolve adaptations suited to the specific environments they inhabit. When environments change gradually, natural selection can track those changes, favoring individuals whose characteristics happen to be better suited to new conditions. But when change exceeds the rate at which adaptation can occur, even highly successful lineages face extinction. The boundary between gradual change that species can adapt to and catastrophic change that causes extinction is not fixed. It depends on generation time, genetic variation, population size, and numerous other factors. Large-bodied animals with slow reproduction, like dinosaurs, are inherently more vulnerable to rapid change than small-bodied animals with fast generation times. Research into dinosaur biodiversity patterns before the extinction reveals that they may have been experiencing gradual decline beginning approximately 76 million years ago, a full 10 million years before the asteroid impact. Statistical analysis of diversification rates across major dinosaur families shows a shift from increasing diversity to declining diversity during the Campanian stage of the late Cretaceous. This decline was driven by increased extinction rates rather than decreased speciation rates, and it appears to have been caused by global temperature cooling of approximately 7 degrees Celsius and changes in herbivore community composition, particularly the dominance of hadrosaurs, which may have outcompete other herbivorous dinosaur groups. The significance of this pre-impact decline is debated. Some researchers argue it made dinosaurs more vulnerable when the asteroid struck, reducing ecosystem resilience at a critical moment. Others contend that sampling biases in the fossil record create the appearance of decline where none existed. What is clear is that even if dinosaurs were declining, they remained diverse and ecologically dominant right up to the moment of impact. The Hell Creek Formation shows abundant dinosaur fossils immediately below the boundary layer and none above it. The extinction was geologically instantaneous regardless of what trends may have preceded it. For modern conservation, this history offers both warnings and guidance. The sixth mass extinction currently underway is entirely different from the asteroid impact. It is gradual, predictable, and caused by human activities rather than external catastrophe. This means it is, in principle, preventable. Unlike dinosaurs, which could not have foreseen or avoided the asteroid, humanity understands the drivers of biodiversity loss and possesses the knowledge and technology to address them. What is lacking is not understanding, but collective will, the commitment to prioritize long-term ecological stability over short-term economic gains. The fossil record demonstrates that ecosystems could appear stable while accumulating hidden vulnerabilities that only manifest during disturbances. Maintaining high species diversity is necessary but not sufficient for resilience. The functional roles species play within ecosystems and the structure of food webs matter as much as species counts. Conservation efforts must therefore focus not just on preserving individual species, but on maintaining intact, functional ecosystems with the redundancy and flexibility needed to withstand unexpected shocks. The story of dinosaurs, their rise, their 165 million year dominance, and their catastrophic extinction is ultimately a story about the contingency of life on Earth. Success in one era does not guarantee survival into the next. Adaptation to specific conditions creates vulnerabilities when those conditions change. And the planet we inhabit has been, and will continue to be, shaped by forces beyond any single species' control. The difference for humanity is that we are the first species capable of recognizing these patterns, understanding their implications, and potentially choosing a different path. Whether we do so will determine not just our own fate, but the fate of countless species that share this planet with us. The statement that dinosaurs went extinct is both true and false. Non-avian dinosaurs, the terrestrial giants that dominated Mesozoic ecosystems for 165 million years, did indeed vanish 66 million years ago, eliminated by the asteroid impact and its catastrophic environmental consequences. But one lineage of dinosaurs survived, the birds. Every sparrow at a backyard feeder, every pigeon in a city square, every eagle soaring overhead is a living dinosaur, a direct descendant of the theropods that stalked Cretaceous forests alongside Tyrannosaurus rex and Velociraptor. The age of dinosaurs did not end, it transformed. This is not metaphor or poetic license. Birds are dinosaurs in the most literal taxonomic sense. They evolved within the theropod lineage, specifically within a group called Maniraptora that includes dromaeosaurs and trudentids as their closest non-avian relatives. The skeletal similarities between birds and their dinosaurian ancestors are extensive and unmistakable: hollow, pneumatized bones riddled with air sacs, gastroliths in the digestive system for grinding food, three-toed feet with a reversed hallux for perching, wishbones formed from fused clavicles, and feathers covering the body. These are not convergent features that evolved independently. They are shared ancestral characteristics inherited from common theropod ancestors. The evolutionary transition from ground-dwelling theropods to flying birds is now one of the best documented transformations in the entire fossil record, rivaling the fish to tetrapod transition in completeness. The lineage began with feathered but flightless dinosaurs like Sinosauropteryx and Caudipteryx from the early Cretaceous of China, covered in protofeathers and pinnaceous feathers used for insulation and display, but incapable of flight. It progressed through four-winged gliders like Microraptor, small dinosaurs with asymmetrical flight feathers on both arms and legs that could glide between trees. It continued with Archaeopteryx, the famous first bird from the late Jurassic that possessed both fully developed flight feathers and wings alongside teeth, clawed fingers, and a long, bony tail. And it culminated in the fully modern birds, Neornites, that emerged during the late Cretaceous and were the only avian lineage to survive the extinction event. The approximately 10,000 species of birds alive today represent more species than all mammals combined. They occupy every continent including Antarctica, exploit habitats from polar regions to tropical rainforests to open oceans, and range in size from the bee hummingbird weighing 2 grams to the ostrich weighing 150 kilograms. This diversity emerged from a single surviving lineage, the birds that made it through the Cretaceous extinction, likely small, ground-dwelling omnivores capable of eating seeds and surviving on limited resources during the post-impact environmental collapse. Research analyzing bird evolution reveals that the transition from dinosaurs to birds involved sustained miniaturization over approximately 50 million years. While most dinosaur lineages maintained relatively constant body sizes or evolved toward larger sizes, the lineage leading to birds underwent continuous size reduction, shrinking from the multi-meter, multi-ton bodies of typical theropods to the chicken-sized proportions of the earliest birds. This miniaturization was accompanied by rapid anatomical innovation, evolutionary changes occurring at rates faster than seen in other dinosaur lineages. The skeleton became lighter through increased pneumatization, the tail reduced from dozens of vertebrae to a short pygostyle, the forelimbs elongated and modified into wings, and the brain enlarged relative to body size, particularly the regions controlling vision, balance, and coordination necessary for flight. Interestingly, while the postcranial skeleton, the bones of the body, limbs, and tail, evolved rapidly during the dinosaur-bird transition, the skull evolved more slowly. Bird skulls are quite similar to those of juvenile. non-avian theropods, suggesting that birds evolved through pedimorphosis, the retention of juvenile characteristics into adulthood. The bird-like features we see today, including large eyes, enlarged brains, and toothless beaks, are in many ways the juvenile features of their dinosaurian ancestors preserved into adulthood through changes in developmental timing. The genetic evidence supporting the dinosaur-bird connection is equally compelling as the fossil record. DNA analysis of modern birds reveals genetic sequences and developmental pathways shared with reptiles, confirming common ancestry. Studies of bird embryology show that chicks develop teeth during early developmental stages before those teeth are reabsorbed, a vestigial feature inherited from toothed dinosaurian ancestors. When scientists manipulated the genetic pathways controlling beak development in chicken embryos, they successfully induced the formation of dinosaur-like snouts with teeth, demonstrating that the genetic information for building dinosaurian features remains latent in modern bird genomes, suppressed but not eliminated by millions of years of evolution. The behaviors exhibited by modern birds also reflect their dinosaurian heritage. Many bird species are now known to engage in behaviors once thought unique to mammals, but clearly present in their theropod ancestors. Brooding, sitting on eggs to incubate them with body heat, is documented in fossils of oviraptorosaurs and trudentids from the Cretaceous, where adults are preserved in death poses crouched over nests with their arms spread to cover eggs, exactly as modern birds brood. Nest building, territorial displays, elaborate courtship rituals, and even tool use observed in modern corvids all have roots extending back into the Mesozoic when non-avian theropods engaged in similar behaviors. The fossil record now documents the progressive transformation of dinosaur features into avian features with remarkable clarity. The grasping, three-fingered hands of predatory theropods became the fused wing bones of birds, with the fingers elongating and consolidating to support flight feathers. The long, muscular tail used for balance during bipedal running shortened progressively, eventually reducing to the pygostyle, a nub of fused vertebrae to which tail feathers attach, creating a control surface for aerial maneuvering. The toothed jaws of carnivorous dinosaurs were replaced by lightweight, keratinous beaks that reduced skull weight and freed the forelimbs from any food-handling duties, allowing complete specialization for flight. The pubic bones of the pelvis rotated backward, creating space for larger digestive organs and egg formation. Each change was adaptive, favored by natural selection, because it enhanced some aspect of survival or reproduction in the lineages that would eventually take to the air. Standing in a park watching pigeons or observing eagles soaring overhead, one is witnessing living dinosaurs, the inheritors of a lineage that has persisted for over 230 million years since the first dinosaurs appeared in the late Triassic. The pigeon's hollow bones are the same adaptation that reduced skeletal weight in Allosaurus and Velociraptor. Their rapid metabolism and elevated body temperature reflect physiological characteristics present in Mesozoic theropods. The feathers covering their bodies evolved first in ground-dwelling dinosaurs tens of millions of years before flight. Every robin's nest built in spring, every goose migrating in autumn, every chicken scratching in the dirt is performing behaviors inherited from Cretaceous ancestors that lived alongside Tyrannosaurus rex. The approximately 10,000 species of living birds represent greater species diversity than all living mammals, making birds, and therefore dinosaurs, one of the most successful vertebrate groups on Earth today. They have colonized every terrestrial habitat and many marine environments, evolved body plans ranging from flightless giants to tiny aerial specialists, and developed behavioral complexity rivaling that of mammals. Far from being evolutionary relics or primitive organisms, birds are highly derived, specialized descendants of dinosaurs whose lineage has continued evolving for 165 million years since their divergence from other theropods. Understanding that birds are dinosaurs fundamentally changes how the extinction 66 million years ago should be understood. The age of dinosaurs did not end. One branch survived, adapted, and flourished. The distinction between dinosaurs and birds is artificial, a linguistic convenience rather than a biological reality. When children are fascinated by dinosaurs and ask whether they still exist, the accurate answer is yes. They see them every day. The sparrows at the feeder, the crows in the trees, the ducks on the pond are all dinosaurs, carrying forward a legacy that began in the Triassic and continues uninterrupted into the present. The age of dinosaurs never ended. It persists in every bird's song, every beating wing, every nest built, and every egg laid. Dinosaurs walked the Earth for 165 million years before the asteroid impact, and they have walked it for 66 million years since. They are still walking it. The story of dinosaurs spans an almost incomprehensible expanse of time, 165 million years from their emergence in the late Triassic to their catastrophic extinction at the end of the Cretaceous. To put this in perspective, the entire history of our species, Homo sapiens, spans only about 300,000 years. The Roman Empire rose and fell in a mere 1,000 years. Human civilization, as we know it, has existed for perhaps 10,000 years. Dinosaurs dominated terrestrial ecosystems for a period 16,500 times longer than recorded human history. During their reign, they witnessed transformations that dwarf anything in human experience. They saw the supercontinent Pangaea fragment into the continents we recognize today. They adapted to climates ranging from ice-free greenhouse conditions with tropical vegetation extending to the poles, to cooler periods with distinct seasonal variations. They survived volcanic eruptions that covered millions of square kilometers with lava, endured sea level changes that flooded and exposed continental margins repeatedly, and thrived through the evolution and diversification of flowering plants that fundamentally restructured terrestrial ecosystems. What makes the dinosaur story particularly poignant is not just their success but the abruptness of their ending. After 165 million years of evolution, diversification, and ecological dominance, after surviving multiple environmental crises and adapting to dramatic changes in Earth's climate and geography, they were eliminated in what was, geologically speaking, an instant. The asteroid that struck 66 million years ago did not target dinosaurs specifically. It simply created environmental conditions beyond the tolerance limits of large-bodied terrestrial animals that required substantial daily food intake. Within years to decades, every non-avian dinosaur on Earth was extinct. Yet the story does not end in extinction. Birds, living dinosaurs, survived the catastrophe and radiated during the Cenozoic to become one of the most diverse vertebrate groups on Earth, with approximately 10,000 species occupying every terrestrial habitat and many marine environments. Every characteristic that made theropod dinosaurs successful, hollow bones, efficient respiratory systems, complex behaviors, parental care, persists in their avian descendants. The robin building a nest, the hawk soaring on thermals, the penguin diving for fish are all dinosaurs, carrying forward a lineage unbroken since the Triassic. The lessons from dinosaur history resonate with particular urgency today. We live in a time when human activities are driving environmental changes at rates comparable to the most dramatic events in geological history. Species extinction rates are elevated 100 to 1,000 times above background levels. Global temperatures are rising. Ecosystems are being restructured by habitat destruction, invasive species, and climate change. The sixth mass extinction is underway, and unlike the asteroid impact that killed the dinosaurs, this extinction is predictable, caused by our own actions, and therefore potentially preventable. The fossil record teaches that success in one era provides no guarantee of survival in the next, that environmental change beyond certain thresholds leads to extinction regardless of prior adaptation, and that recovery from mass extinctions takes millions of years. But it also teaches that life is resilient, that from catastrophe comes opportunity, that empty niches are filled by survivors, and that evolution continues regardless of what disasters befall individual species. The question facing humanity is not whether Earth and life will endure, they will, but whether we will be among the survivors or the casualties, and what kind of world we will leave for whatever comes after.